We'll give it a little more time and then we'll get started. Okay, let's get started. So, welcome everyone to this training on Julia. Um, the aim of the training is in fact to see whether Julia is something for you, whether it would be a useful tool for your scientific computing. And so basically I will be making quite some comparisons with other languages. So just to highlight things that Julia is very good at, that I'm not so fond of, and that I find, well, not so elegant, let's put it that way. So these, of course, are personal opinions based on some experience, obviously, but of course, it doesn't mean that if I like a feature, dislike a feature, or think that something is really, really ugly, that you necessarily need to agree with you, in the sense that, of course, for you, that particular feature might or might not make a lot of sense. So in that respect, um, just view this training in perspective. It is sort of a introduction to Julia, um, mainly to see whether it's interesting or not. Okay, so what I'm going to do before we really get started is to do a small poll, because as I mentioned, I will be making comparisons with other programming languages. So for me, it's useful to know what programming language you mainly use. And there are, of course, several options. And unfortunately, I can only put 5 options here, so I have to be a little bit selective. Okay, so let's start the poll. And okay, so that means you see the reactions. All right, so if you don't see your programming language and you think it is relevant, then feel free to type it in the chat. Then I can see that as well. Okay, let's conclude the poll. Oh, and now it vanished. Damn it. Okay. That was stupid. I thought I would stop the reactions and that it would still show, but now it disappeared. Okay, anyway, most of you actually are using Python. There are a few people coming from Fortran, less from R and MATLAB if memory serves, and yeah, that's probably it because there was no one using C++. Okay, good. So I will be making mainly comparisons with Python, R, and MATLAB, and now and again a remark about Fortran. Okay, excellent. Now let me share my screen so that we can really get started. There we are. And that takes a minute. There we go. Okay. So, first of all, if you have any questions, feel free to type it in the chat. I'll keep the chat visible so that I can actually see your questions. Okay, and so feel free to type a question at any point. If I don't understand your question, I probably will ask you to activate your microphone and to just ask a question verbally or elaborate verbally. Okay, the more interactive this is, the more pleasant it is for me. And of course, the more useful it is potentially for you. So again, feel free to ask questions at any time. All right, so this is a QR code, which you can happily ignore because I'm going to post the corresponding link in the chat for your convenience. But I do want to say something about it, and hence the slide is still useful even in an online setting. So basically, this is a link to a repository, well, actually to a website concerning this training, and that would be the website. So there is the usual stuff like learning outcomes, blah, 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 all that kind of thing. The schedule, which I probably won't keep to anyway, but more or less. And actually, more importantly, there is also a button here at the top, which is View on GitHub. And that will bring you to this repository in which you will find the slides which I'm using, which is here, or which are here. You will also find an environment definition file if you want to do this using Conda. If you want to install Julia using Conda, that's an option. Not the one I'm using, but it's quite possible. Probably there's also some stuff in there for some data processing, which I'm doing not in Julia or something like that, but rather in Python. And what is also quite interesting is a directory of source code. And basically all the code I'm showing in the slides is somewhere in the source code directory. Because of course, slides don't come out of the blue. They're the result of experimenting and running code. So basically that code you can actually find in this repository. So feel free to clone the repository or fork it, depending on what you like to do with it. It's publicly available. There is a license, but it's a very liberal one. Okay, with that out of the way, let's continue. And basically, this is might be a good idea. Connect to us on via LinkedIn, because then we keep you current through that channel of trainings which we organize, other events, and news in general about supercomputing. So feel free to connect with us, to follow us on social media. All right, so we are getting closer to real start, and basically some typographical conventions about the slides. So inline code fragments and file names are rendered in this somewhat ugly font to make them stand out from the rest of the text. Larger code fragments are always in the same ugly font, but rendered on a grayish background. For data files, I use a greenish, yellowish, whateverish background, but distinct from the gray one. So just to make clear that it's a data file and not a code file we're looking at. And what you will see from time to time is these ellipses here, the triple dots, that has nothing to do with either Julia nor our data files. Sorry, but everything with screen real estate and the fact that a slide has a finite width and height. So basically that's just to indicate that there should be more stuff, but that there is no place to actually put it, which means in the case of code that actually it was either already explained on a previous slide, or it will be explained on the next slide, or it should be really, really straightforward to imagine what is going there. For data files, it just means, okay, there's more of the same. All right. Then if we do something in the terminal, I really don't, then the terminal output is rendered as white on black. So basically to just visually make clear that that is something that has been printed by our code and that it's what would appear on your screen if you would run a certain code fragment. Okay, we'll also have a thumbs up for good practice and we have a thumbs down for bad practice. Okay, so these are some conventions used throughout the slides. Okay, some impressions, high-level impressions about Julia. So it's pretty clear when you come from a MATLAB background that Julia has taken some inspiration, to put it mildly, from MATLAB. And that, of course, is, depending on your opinion of MATLAB, a good thing or a bad thing. At any rate, it's pretty clear that Julia tries to cater to the people who would be inclined to use MATLAB or who are using MATLAB and are trying to find an alternative to switch to. And Julia might be one. It's one which, as a MATLAB user, you might consider to switch to. Because many things will actually seem quite familiar. And a big advantage is that Julia is an open source software, which is free to use, while MATLAB is, well, closed software and basically not exactly free to use, to put it mildly. Of course, your institute may have a campus license, in which case it seems free to use, but yeah, that is obviously because the taxpayer is footing the bill and not your particular research group. So essentially, it's a pretty expensive hobby to work with MATLAB. Okay, if I look at it, and I'll come back to that later on with a concrete example. So Julia tries to mimic mathematical notation, but it only goes so far, and that so far is not very far, which for me makes it look a little bit, how should I put it, a little bit shabby attempt at doing things right. Okay, that's easy to say because many other programming languages don't make any effort in that direction at all, which is true. But on the other hand, I know that it's possible to do it right because, for instance, something like Wolfram Mathematica actually does that right, does the mathematical notation stuff way better than Julia. So in that respect, yeah, sorry, it's half-baked. I'll show you what I mean by it later on in the slides. So Julia is not object-oriented, and it uses a different mechanism for specialization under the hood, rather than, well, under the hood, and you would also use it for doing, let's say, larger scale programming, where you would normally, if you use an object-oriented language, start using classes and objects. So Julia chooses a different approach, and that is not a good thing, not a bad thing. It's just a choice, which is interesting. And if you come from background, programming background, where, to put it mildly, object orientation is the standard thing you do if you start large-scale programs, C++, Fortran, Python, you would use object orientation. But in Julia, that's not available. So it takes a bit of a, how shall I put it? It's a bit of a learning curve to switch the way you think about software design from object orientation to multiple dispatch functions. But once you get the hang of it, it's rather nice. It is often claimed that that is actually making Julia superior to the traditional object-oriented languages like Python and like C, C++, well, no, not C, C++, Fortran, and so on. I would claim that that was true as long as Julia's ecosystem was pretty small, and now they face the exact same problems as the people from other languages face. So that was, in my opinion, just an illusion based on a very small ecosystem. In a very small ecosystem, you have few problems. As soon as your ecosystem starts to blow up, the problems blow up not proportionally, but by an even larger exponent. Let's put it that way. If at least we assume that the problems are polynomic, are polynomially increasing with the size of the ecosystem. R people are pretty much aware of that. The R ecosystem is tedious, to put it that way, because it's so huge. All right, then it has a very nice typing system. I like that a lot. So Julia is a strongly typed language with type inference. So basically, you don't necessarily need to specify types. Actually, many people specify types in Julia inappropriately, where they really shouldn't, because they think they should. No, there are good reasons to add typing information in Julia, and there are excellent reasons in some occasions not to do that. So that's also something that we will discuss. But the advantage of having a strong type system is basically that it allows the compiler to do pretty nifty and powerful optimizations. So you get pretty efficient code thanks to that kind of design of the language. So that's definitely a very good thing. The package system is something I also appreciate because it comes with Julia. It's built in. If you look at the Python side of things, then of course you have many package managers. You have things like Conda. You can, if you want, use venv or other tools to actually make sure that you have separate environments for projects or for programming tasks, which is very good practice and which I can only encourage. So I'm quite happy to see that in Julia, environments are actually first-class citizens in the sense that they are built into the core of the language. And that is a very good thing. Then we have some design decisions which are, let's say, interesting. And we'll come across quite a few. And I'll express my opinion on them again. Take it with a grain of salt because they are my opinions. So basically, that is to be taken with a grain of salt. Okay, so there is already a question which I missed. I'm going to put the sound a little higher because it's pretty high. Why don't I hear it? Okay, no, we'll see. Anyway, so question is there absolutely no class objects available in Julia? No, there are no classes, there are no objects. There are types, but that's a somewhat different story. So functional programming, it also class creation. Yes, exactly. So Python is from the ground up an object-oriented programming language. Yes, it allows for functional programming, that's true, but everything in Python is an object. An integer is an object. A floating point number is an object. So that is very different with respect to, for instance, say Java, say C++, say Fortran, where all these types, all the numeric types, all the character types, the Boolean type, and so on, all the values in those languages are primitive values. It is to say, things that are definitely not objects, while in Python, anything is an object. The value true is in fact an object. So basically, Python is really very much object-oriented, even if you use it in a functional style, while that's absolutely not the case for Julia. In Julia, there are no objects. Does Julia compile to native code? Yes. So basically, what is happening under the hood is when you write your Julia functions, your Julia code, and you execute that, either whether it's in a Julia script or whether it's in a notebook, what happens under the hood is that code is parsed. There is an abstract representation made of that code. That abstract representation is then used by a compiler to generate assembly code. So basically to generate machine instructions that run natively on the CPU you're using, which indeed opens up the second part of the question, which is, okay, what does it run on? Basically on everything you'd normally use. So essentially you can run Julia happily on your Windows machine. You can run it on Linux. You can run it on macOS. So anything normal, it will actually run on. Will it run on something with an ARM processor? I don't know. But I don't have one, and it's somewhat unlikely that within this year you would have access to a system that actually runs on ARM processors. So you can consider rather safely Julia as cross-platform, and the compilation is done in time. So basically that means compilation is only done on the system you're running on. So that also means that if you install a Julia package and you use it for the first time, it will take a while because it will actually be compiled into assembly code that runs on your specific CPU. Okay. All right, so these are just some high-level impressions of the language. And again, well, it's personal opinion. Okay, so how do we run Julia? So basically, we can run it in an interpreter mode, which you can sort of compare to MATLAB just by calling it on the command line. So if I were to do that, do I have an interpreter open? Yes, I do. Well, a shell open, I do. So let me prepare that a bit. I've been doing different things here. Let's open up a new tab. Let's just close this one to avoid confusion. Let's increase the font size. Let's try and get this thing centered. And here's my terminal. Oh, that was not the plan. Okay, and let me move this a bit. Okay, now at least I can resize it. I really have to spend a little time figuring out how I can get the default of an opening window not to be outside of my screen, but okay. All right, so now we've got something that is usable, I think. Yeah, that's good. Okay, so basically, indeed, you just type Julia, and it is going to start. In this case, I'm running with what is probably the latest version, which is 1.10.1. So now I can start typing Julia commands, which are of course very exciting, such as 3 + 5, and indeed I get 8 as a result. So this is one way of running Julia. You can also run a notebook, and then actually in your session, you just type using iJulia, which I hope I have installed. So no, apparently I don't. Yeah, package iJulia not found, and I'm spelling this correctly, I hope. Yeah. So basically I should install it. So basically it happily tells me how to do that. So that's convenient. Okay. But it is not happy. For some reason, import error, the following package names. Okay, yeah, I think actually that there is a typo on the slide and that this should be a capital J, but let's try this. Yeah, that's better. Okay, so indeed, I was already suspicious. The lowercase j seemed not that correct. So most likely, this was our good friend PowerPoint, Microsoft PowerPoint, being smarter than me and thinking that you can not have two capital characters at the start of a word. Anyway, I'm making a note to actually fix that later on in the slides. Okay, so once the thing is installed, and if you're asking yourself why this is being installed right now, basically because I installed this version of Julia pretty recently. So in an older version, I had the notebook environment installed, but not here. Okay, so this will take a while. Let's just continue and we'll see how it works later on. So indeed, this was the first time I tried to run it. It couldn't run because it wasn't there, and it suggested on how to install it. So yeah, that was easy. Okay, you can also run scripts just from the command line. So basically, the extension .gl indicates it's a Julia file. Of course, like anything in Linux, you don't have to bother about the extension. Linux doesn't care about it here, but it's convention to have the .jl extension for Julia files. Okay, so meanwhile, okay, so normally now I should be able to start notebook. Let's see. Okay, notebook not defined. All right, what did I do? It's a function, yeah, of course. Okay, so, right. Okay, now I don't know. That's weird.
Yeah, and I think you have to run using iJulia again first.
Yeah, because that was of course not done. Yes, true. Thank you. No, that did not succeed, and now probably I can happily run notebook. Yes, now it runs. Yeah, okay, indeed, I wasn't following my own slides, so basically, but it still doesn't work because set end, blah, then Jupyter Notebook. Okay, I would have to probably install. Oh, there it. Damn it. Yeah, okay. Yeah, this is a annoying notebook thing. Okay, let me exit this. So I exit this using Control D, and okay, so I would have to, because it's using a version of Jupyter Lab, which ought to be installed in the environment I'm running in. I'm running in my base environment, and of course there is no Jupyter there. So let's have a look. at some environments which I have installed, and what did I do? Envlist, of course, and which would contain a notebook. I'm going for the simplest one possible, given that I have a million of them. That's not so easy to determine, but normally Python for programmers should be a fairly minimal one. Okay, so Mamba activate with the name of the environment, whatever it is. And now let's start Julia again. Let's using iJulia. Let's notebook. And now it can actually find Jupyter Lab, and it is going to run a notebook here, as you can see. Unfortunately, that is Jupyter Notebook and not Jupyter Lab. So yeah, it's a trip down memory lane for me because I prefer to use Jupyter Lab since a couple of years. But anyway, so it would work. And of course, I can start, I should do that. I can start a new notebook with a kernel, which I choose, which in this case is Julia. Okay, and again, I can start typing Julia commands and executing them as usual in SL, hitting Shift Return. And then it takes a while before it actually starts the kernel, which I hope is working and not crashing. No, that should be okay. Nothing is happening here. So it just takes a while until it warms up and actually does something. Okay. Migration plan to notebook 7. Oh my god. Okay. Yeah, this I'll have a look at later. Okay, this seems to take like forever, which is kind of annoying. Okay, that might be some compatibility thing somewhere. Okay, we get 8. We just need a lot of patience, that's all. Would that work? I don't know. Let's have a look. That's an interesting question. So I'm going to quit this thing here. I need a little bit of more real estate. No, I can actually. Where is it? Close and hold. Okay. No kernel. Yes, and now I can close this and come on. Yes, I want to leave this and I want to quit. Let's try whether indeed Jupyter Lab would work. Yeah, it seems to do something and it's calling Jupyter Lab. Okay, that's pretty great. All right, so yeah, much more familiar. And indeed, I can start a new notebook. It is likely not going to be faster, but so basically, the time this takes is the kernel spinning up. If I do it a second time with 3 times 10, for instance, then I get an answer immediately. Okay, that's good. I will add that to the slides. That is very useful because, as I said, I'm not a particular big fan of Jupyter Notebooks. Right. Okay, so basically, let's turn to Julia expressions. So there are quite a number of operators, and the assignment operator is just the equality sign. So for the R people, you can use a left pointing arrow or even a right pointing arrow for assignment, or the equality sign for assignment. Here it's just the equality operator, nothing more. Arithmetic operations, no surprises for addition, subtraction, multiplication, division. The power operator is the caret, So that is similar to MATLAB. In Python, that would be the double star. So yeah, it has all these operators, so that's quite good. You also have integer division, and you can do that in two ways. Either you can use the diff function, which is, let's say, prefix notation, or you can use the operator, the infix operator, and that is the, yeah, whatever that thing is called, basically a division sign, I would say. So how do you get that in Jupyter Notebook? Well, what I can do is say, well, okay, I'm dividing 5 by 3. So I type /diff, and I hit the tab key. And then this turns into this particular sign, and I can do integer division. Okay, I get 1, as I would expect. If I do 5 divided by 3, then I get a double precision number, so basically a floating point value. So in that respect, it's quite similar to Python. In Python, of course, the division operator is double slash. So for Fortran, if you divide two integers, you also get an integer. So basically that's the same. There is no operator in Fortran which takes two integers and gives you the floating point value. Then you have to convert one of them to floating point, and then you can actually do that division. Okay, so those are your basic arithmetic operators. I would say no surprises, except perhaps for the infix division. All right, comparison operators. Again, nothing much special. You have a bit of a choice for non-equal. You can either use the version which you're used to from Python or from sorry, C or C++, which is exclamation mark equals, or you can use not equal. And of course, you have already recognized that basically this is the same notation which you would use in LaTeX. So for instance, I could do something like 5 not equal. Again, I type the tab 3, that should evaluate to true, and indeed it does. And that would be the same as this expression. It does the exact same thing. So which you prefer depends a little bit on the environment you're in and what editing commands you have at your disposal. If you write a Julia script, I would suggest to go with the more classic notation. On the other hand, if you are in a notebook, then of course you can use these fancy symbols in order to remain closer to mathematical notation. Similarly, for less than or equal, you can either do that with a less than character followed by an equal sign, or you can have this fancy notation, similar for larger than or equal to. Okay, so there are not many surprises, some of them. So equality, test for equality is done by double equality sign. If you want to check object identity, yeah, okay. So basically, if you want to check that two things are really the same, so object identity is a bit of a misnomer in Julia, but then you can use the triple equality sign, which would be the is operator in Python. Logical operators. So again, I don't think there are any surprises. We have the exclamation mark for not, double ampersand for logical and double pipe for logical or. So no surprises. You can also do function composition, and for that you need the circle operator. So basically that's \circ followed by a tab, and that allows you to concatenate or rather to compose functions, apply one after the other. You can do piping with the the vertical pipe followed by a larger than sign. Okay, we'll see some examples of that later. Now, what is equivalent is 2 times a variable written as 2x, and that is the same as 2 times x. So just to show that, suppose that I assign something to a variable. Let's say that I assign 2 to it. I can happily write 2x, and that will evaluate to 4. However, if I also have y and I assign 3 to it, something like xy, which you would expect to work if you are used to Mathematica, is going to horribly fail, and you get an error message that this is actually nonsense, extra tokens at the end of expression. Julia really doesn't know what to do with this. So basically, that is not going to work. And that's exactly what I meant by a half-baked mathematical notation. So yeah, this is cute that you can do it, but the usefulness of this is more or less limited by the fact that it only works for real numeric expressions. So yeah, well, I fail to be impressed, but that's me being obsessive compulsive, because yeah, if you go that far, why don't you go all the way and write a proper parser for your language? But well, who am I? Okay, so a few naming conventions. Basically, variable names, there are not that many surprises. So basically, variable names can be any thing you want, in the sense that they should be character-based, no, letter-based. So the first character should always be a letter, and then it can be followed by, of course, more letters. It can be, it can have digits, and so on. You can use Greek characters, for instance, as variables, which you, by the way, can also do in Python, but it would be actually the exact same thing. Now this is the variable alpha. I can assign 3.5 to it, and of course I could do something like 4 times alpha. Okay, so all of this works. It's nice. I also tend to do that sometimes in Python when I'm using notebooks for educational purposes. If you're talking physics, then it's useful to use Greek letters to denote certain quantities, because that's what you're familiar with if you open a textbook. Okay, of course, variable names can be uppercase. So what I mean by variable names lowercase is that it's the convention to have them in lowercase. That also means that uppercase and lowercase are not equivalent. So the Fortran people have to take care a little bit. An uppercase A is not a lowercase a, as is the case in Fortran. And if your variable name consists of multiple words, they should be separated by underscore. So that is actually the same convention which we have in Python. There is no difference there. Okay, function names can also be Unicode. So alpha can also be the name of a function. Again, they should be lowercase, just convention. And words are separated by underscores as well. And there's one additional convention which is a bit odd when you come from a different background, and that is that if a function modifies its argument, by convention you append an exclamation mark to it. So that's just to warn that a function is going to change its arguments. We'll come back to semantics of function calls later on, but you can already guess that this means that Julia supports call by reference rather than call by value. Okay, types. Again, they can be Unicode, anything you want, but typically there is a different convention. They're camel case. So basically, if you have words, each of those words is starting with a capital letter. So for instance, float would start with a capital letter if float is a type, which we'll see it sort of is. Okay, so you may not want to use Unicode names so the special character stuff, in names that are user-facing. What do I mean by that? The problem is that if I create a function alpha, which is supposed to be called by a user, and that user happens to be in a terminal where it is freakishly difficult to get an alpha character typed, you are not going to make that person happy. So I would say for libraries, library development, don't do that kind of thing. It's probably you're going to make people unhappy, which is a bad idea if you want your code to be used. Of course, as usual, follow the conventions which are prevalent in the community. So basically, these are the conventions which the Julia developers recommend. So I would suggest that you follow them as well. Okay, functions and methods. Yeah, methods. Whoa, are we going object orientation anyway? Well, it has a different meaning. So let's see. We have a function, and in this particular case, it's a very boring function. So basically, it takes 3 arguments, x, a, and b, and the name of the function is linear scale. We indicate that this is a function definition by using function end. So between function and end is the body of the function, in this case 2 statements, of which one is pretty stupid. The term is equal to a times x. Of course, makes 0 sense. I would normally write return ax plus b, but it's just to show that there can be multiple statements within a function body, which is fairly obvious, but okay, let's just point it out. So the first line obviously is the function signature, the name of the function, and the arguments which are to be provided to the function, and anything in the function is enclosed between function and end. So if that reminds you of Fortran, yeah, that's probably not a coincidence, because it's the same there. And also in MATLAB, you have this end thing. So no curly brackets, no indentation to denote the structure of your code, space, white space as in Python, or curly brackets as in JavaScript, C, C++, etc., etc. No, it's good old-fashioned Fortran-like notation with ending a block. So this would actually be the same thing as term is equal a times b, term plus b. So the value of the last statement is actually going to be the return value. So whether you write return or not, the result is going to be the same. That's actually the case in quite a number of programming languages. Typically, I prefer, for clarity, to have a return statement, an explicit return statement. But yeah, that's a personal opinion. That is not something that is accepted by everyone. And for instance, in MATLAB, you would also have the same, well, you would not have the same thing. You would actually assign to an output variable. So how do you prefer to return 2 values? Oh, you can create data types such as tuples and so on, and that would be a way to return multiple values. Okay. Very short functions need not have function body end. They can just be defined like this. So we just give the name of the function, the argument names, and then we just assign the body of the function to that in a way. So you could compare this quite well with what happens in Python with a lambda function, which would also just be an expression in a single line of code. Okay. So you can also have real lambda functions, in the sense functions without a name. And basically the notation is slightly different. So you have a tuple of arguments, and then the arrow operator gives the body of that particular Lambda function. So yes, Lambda functions exist, and they can be useful, as we will see later. Okay, so in Python we have optional and keyword arguments. Does namespace module system? Yeah, so basically let's return to that because I'm going to discuss that. In general, it's a little bit the same as with any programming, well, any modern programming language like Python and C++, and also Fortran. If you just do the equivalent of a blind import, you will get, you will what's the word? You will mess up your default namespace. So just like it's bad practice to do something like in Python from NumPy import star, yeah, never do that. It's a really bad idea. So you can do the equivalent in Julia, but as in Python, yeah, please don't, because no, it's not a good idea. Yeah, there are ways to modelize your code, and we'll come back to that later on. So no worries, we'll talk about it. Okay, so in Python, you know that you can have keyword arguments that denote optional values, and it's very similar here in Julia. So x and y, we will need to give a value, and we can optionally give a value to delta. If we don't, it will just have the default value of 10 to the power -5. Okay, so this function essentially would implement a sort of almost equal. So if x and y in absolute value are less than a certain delta, then they are considered to be equal. So I would do almost equal AB, and then of course that would mean that A and B are compared up to 10 to the -5, or I can specify an explicit value for delta, in this case 10 to the -3. You also have keyword arguments as such. However, there is a difference with Python in the sense that you have to separate keyword arguments from positional arguments by a semicolon. So that means that EPS and UPS are in fact keyword arguments, and I would have to call them as such as well. So basically I can call almost equal again with just x and y, and then if I want to provide one of the keyword arguments, I'd have to do that by name. So basically it's similar to Python. The only thing you have to remember, if something is really intended to be a keyword argument, it should be after this semicolon thing. I've got a bit on the right. Yes, that is possible. That's although, is that possible? It should not be. It should scale. No, it scales. It isn't cut. It isn't cut. It should be all right. No, because I'm really in presentation mode. So normally my slides get scaled so that they fit. That's why. That's also why I have the black bars here at top and at the bottom, because of course these are the slides which are in whatever it is, 9 to 16 or 10 to 16, whatever the ratio is, and of course that doesn't fit my current layout of the application. So that's why I have the bars. But normally it should really fit. Okay. So now to multiple dispatch. Yeah, another question. Okay, this I don't get, but I'm going to pass on this one. I don't quite get what you mean by the video is smaller on one side of the monitor. Okay, that seems weird, but okay, doesn't matter. Split. Okay. Right. So let's move on to multiple dispatch, because that actually makes things interesting, and that actually allows for large-scale software development in Julia, which would otherwise be very challenging, which is still challenging, just like it is in object-oriented programming, only different challenge, different mindset. So what we can do is define multiple versions of the same function based on its signature. So we have a function show type, whatever, and now we specify the type of the argument. Don't worry, we'll come back to the family of types later on. It's one of the next slides. But we have an argument x, and that is really supposed to be an integer. And if that's the case, then I print the value of x, and I say that it's an integer value. Okay, so there are a few new things on this slide, so let's go through them. The first one is the type annotation. So this is the way in Julia to declare that x must be an integer. And so basically it's the name of the variable followed by double colon and the name of the type. The next thing that's new is the println function. So you can probably guess what it does. It will write to standard out, and at the end of the string, it's going to append a new line. So it's outputting a line of string, whatever is in the string. And then you also see that we get substitution of values. And basically the notation is similar to bash. So essentially $x means give me the value give me the value of the variable x, and that is what is going to be printed. Well, part of the string which is going to be printed. So in Python, I would have to use an f string here, and I'd have to enclose x in curly brackets, and I would get the exact same effect. So in that respect, I would argue that Julia is a little easier because I don't need to remember that I have to use an f string, which is, okay, not a big thing, but it's easy to forget to do. And of course, you save a little bit on typing because you don't have to use a closing curly bracket here. You just have to use a single character, which is the $sign. Okay, apart from that, you can argue whether it's useful or not, or whether it's better or not. But now back to multiple dispatch. So now I define a second version of the function, show type, that has the same name, but it has a different argument in the sense that the type is different. So rather than being an integer, this function will be called whenever x is a real value. And apart from that, the same thing happens. It's going to print, but now it's going to print its real value. So now I have two versions of this particular function, and depending on the argument, either one or the other is going to be called. So if I do show type 5, of course you can guess that the integer version is going to be called. If I do show type 5.0, then of course the real value is going to be called. So basically that also means that what I typically tell people when I talk about programming in whatever programming language, be it Fortran, C++, Python, you name it, I always tell people, well, okay, if I intend something to be a floating point number, I'll always add .0 after it. Yeah, I know the compiler is usually going to do the right thing, etc., etc. Not always. Type promotion, blah, 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 all kind of issues with compilers, but okay. But typically it's good practice to really make sure that if you intend something to be a floating point number, that you visually indicate that by adding a .0. Okay, now in Julia, that's even more important because it will determine which version of a function is actually called. So it's really a hard requirement here that you add the .0 to floating point constants. Otherwise, you will have well, you won't have the function call which you actually want to be made. So what is very important to realize is that you should only use type annotations for multiple dispatch. Many people who start using Julia will use type annotations regardless, even if it's for a function where there is no multiple dispatch going on, because they think, yeah, I give more information to the compiler and hence my code will run faster. Well, no, that's unfortunately a bit of an illusion, because the compiler is going to generate specific code anyway. If I call a function with an integer, it might generate different code than if I'm going to call that function with a floating point value, where it might generate different code. So multiple versions of the same function will be generated by the compiler anyway, only they will be generated as needed, and hence you will actually typically, or you might even get better performance. So that's what I mean when I say, okay, only do type annotations in Julia when you require them for multiple dispatch. Otherwise, let the compiler do its thing. It typically knows better, so just let it do its magic. Okay, so we can also deal with a variable number of arguments, and that would be using this notation. So this function takes at least two arguments, x and delta. And in this case, I succumbed to the temptation to actually use the delta character rather than delta explicitly. And then we have values. And values, in fact, is going to be a tuple of 0 or more arguments. Any number of arguments can be passed here. So what is going to happen? I'm going to do something that is extremely familiar to Python people. Let's read it from the inside out. So values is a tuple, so something that I can iterate over. Okay, what am I going to do with it? I'm going to map. And map applies a function to each value of something I can iterate over, and it returns that value as an iterator. So in this case, you already recognize the syntax. So basically, this is a lambda function. It takes a single argument, and it will return the absolute value of the difference between that value and x, and it will compare that to delta. Okay, so map is going to produce a sequence of Boolean values. Just a second, sorry.
Hier?
Ja.
Voilà. Merci.
Thank you very much.
Bye.
Apologies, some delivery thing. The map produces a sequence of true and false values, so of Boolean values, and if all of them are true, then all will actually evaluate to true. If any of the Boolean values is false, all is going to evaluate to false. So yeah, Python people know the all function, they know the map function, so basically this is very familiar to you. Also in Fortran, we have an all. We don't have a map, but the all actually is there. So this is a very familiar expression. So how can I call this function? Because this is not so much about functional programming in Julia as it is about dealing with the multiple arguments. So basically, I could call the function like this. Then 0 is going to be assigned to x. A delta is going to be 10 to the power minus 5. And then I have two values, which are in values. So value is going to be a tuple. I can also call it with only 3 values. And then, of course, there's only one argument in tuple. So that's the way I can actually deal with an arbitrary number of arguments, a variable number of arguments in my function signature. Okay. So that was a little bit about functions. We will come back to some other aspects later on. Let's talk a little bit about control flow. So, of course, like any programming language, there will be conditional statements. And of course, that's the if-else statement. So there are, I would say, a few potential surprises. So basically, if you have an if, the Boolean condition for that if does not need to be enclosed in round brackets. Fortran people would do that, Python people would not. Basically, you don't have to. Also, there is no such thing as then, like you would have in Fortran. So basically, you have the if statement, and then you have the statements in the body. So this function, as you can guess, is going to compute the factorial of n. So if n is negative, of course, I can't do that. So I indicate that an error occurs, and I can do that using the error function. So this is a basic, well, built-in Julia function, and that is going to write fact argument must be positive to standard error. Okay, then if we have an else if, the syntax is again a little bit different from other languages. So it's really else if. So not something like elif or else if without an e and things like that. Not else space if. This is the syntax. Can't help it. That's the way it is. Okay, and then we just have else with some computation and. So we always have if and. In this case, we have if and if, else if, else and, but we always have the pair if and. Okay. You can use logical shortcuts or short circuiting, as it is also called. So that's something that you might be familiar with from Python. Python is one of the programming languages that support it. You're probably even more familiar with it if you have a background in Bash, but you can also do this in Julia. Whether you should do this or not is basically up to you. Personally, I've never really gone into the habit of doing this. So yeah, I'm not necessarily a very big fan of this, but let's run through it and see what happens. So what we are relying on in this case is that Boolean evaluation of operators is lazy. So what does that mean? It means that if the first operand of an or let me call it the left-hand operand of an or, evaluates to true, then the second operand is not evaluated because the or statement will evaluate to true anyway. So if the left-hand operand is true in an or, the right-hand operand must not be evaluated. Okay, so that means that if n is negative, strictly negative, then of course the left-hand operand evaluates to false. So to check whether the or statement is in fact true, I would have to evaluate the right-hand operand. So I'm going to execute the error function. So my function terminates and writes something to standard error. Okay. If, on the other hand, n is positive, then the left-hand side operator of the or evaluates to true. The right hand is not evaluated. Okay, so we go to the next statement. Then again, we check whether n is smaller than or equal to 1. If that's true, then we don't know anything yet, because this is the left-hand operand of an AND. So basically, if the left-hand operand is true, we still have to check the right-hand operand in order to make sure that the whole AND expression evaluates to true. So then we'll evaluate the right hand, which means return 1. Okay, function terminates with the return value 1. And then finally, we have a return. Well, okay, suppose that n is larger than 1. Then, of course, the left-hand operand of the logical AND evaluates to false. And I don't care about the right-hand operand because the AND will be false anyway. So the return is not executed, and we go to the next statement. And the next statement is a recursive call to the factorial. Okay, so I've tried to run through it. Let's do it again. We have a number of cases. Suppose that we call factorial with a negative number. So n is, for example, -1. Okay, so we evaluate the first statement. The first statement is an OR statement. Okay, operands are always evaluated first left, then right. Okay, so we evaluate the left-hand operand. Okay, -1 is not larger than or equal to 0. So this evaluates to false. Okay, we have a logical OR. This might still evaluate to true if the right-hand operand evaluates to true. So that means the arrow function is executed. Okay, but the arrow function prints something to standard error, the message which we specify, and it terminates the function. End of story. If we call factorial with -1, it will exit with an error. Okay, that was case number 1. Case number 2, we call the function with either 0 or 1. Let's say with 0. Okay, so in this case, we check whether 0 is larger than or equal to 0. That happens to be true. But that means that this OR statement is true already, because a logical OR is true when one of its operands is true. So if the left-hand operand is true, I don't need to check the right-hand operand. So the error function is not ever called in that case. All right, so that's the first statement. The second statement is an AND. So 0 is less than or equal to 1. So this is true. But an AND statement is only true when both operands are true. So I have to evaluate the right-hand side operand, which is return 1. Okay, end of story, because the factorial will return 1 if it's called with n equals to 0. Same story for 1. If I have n larger than 1, say 5, then again we have 5 larger than equal to 0. Okay, the OR statement is true, or the OR expression evaluates to true. So error is not done. Then here we have 5 is less than or equal to 1, but that is false. So there's no way that the AND expression can evaluate to true. So we don't need to bother with the return 1 because it's not relevant. The AND expression is already false. So we continue, and then we get to the last statement, which says, okay, call the function again with n minus 1, so with 4, and multiply by 5. Okay, so that's basically the idea. Yeah, exactly. So the key here is the lazy evaluation of logical operators, of the logical AND and the logical NOT. And as soon as you evaluate the left-hand operand and a decision can be made about the whole expression, you stop. So that means that if n is larger than 0, the error is never executed. If n is less than or equal to 1, the return statement is always executed. If n, on the other hand, is larger than 1, the return 1 is not executed because the end expression cannot evaluate to true anymore. So that's basically the idea. Is there any benefit? It's a matter of style. So I'm fairly certain that the same code is being generated. I'd actually have to try this in C++ and see what code is generated for that language. But I think that there will be very little difference in the code. So it's mostly a matter of style. There are people who really appreciate the second way of writing code. Personally, again, I'm not a big fan, but it's a matter of taste. Well, basically, it doesn't even really matter whether they can be converted to Boolean values or not. It's just that they will or will not be executed, and it's their effect we're interested in, not the value which they win. So again, it's the code equally fast if you write them in the style which most of you are used to, or in this particular style which is a bit peculiar. The answer is, I think that the machine code which is generated is very much the same. So I don't expect a performance benefit of either style. It's a matter of coding style. It's a matter of what you are familiar with, or what is the culture in your development environment. So basically, in your research group or whatever, or your company, whatever you are working on. Indeed, you could say that the second approach is a bit more mathematical in a way. Yeah, that could be interpreted that way. It's also more familiar to people who do a lot of shell programming. They would also use this quite a lot. I do in shell scripts, but not really in Python or in C++. Well, in C++, no, also not. Yeah, so I tend not to do that in Julia either. For me, it's a shell thing. But again, it's a matter of style. Okay, repetition. So basically, we have a while loop, and I don't think there are any surprises here. So this code will compute the greatest common divisor of A and B using Euclid's algorithm, and essentially there are no surprises. You have a while with a Boolean condition. Again, the Boolean condition need not be within brackets, and then you have an end statement which encloses the body of the while. Okay. Very unsurprising. You have break, you have continue, and yes, they have those names. The semantics are the exact same as in Python. The names are the exact same as in Python. For the Fortran people, break is exit and continue is cycle. So you have the same things, only they have different names in Fortran. Apart from that, I would say absolutely zero surprise. You also have a false statement, which again resembles a do loop in Fortran a bit, a for loop in Python a bit. So it's somewhat a mixture of the two, I would say. There is some MATLAB there as well. So yeah, this is a somewhat bizarre mix. So this would of course be the implementation of the factorial function, but not recursively, as would be not your smartest approach, but rather iteratively using a product rather than recursion. So the fourth statement is the one which we're interested in. So the variable of the for loop will be I. and we use the syntax which you're familiar with from Python. So the in keyword here, and then we have 2 n, and that's of course very familiar to MATLAB users, because that means generate me a sequence of numbers between 2 and n inclusive. So Python people, please don't get confused. If n is 5, I will have the values 2, 3, 4, and 5. So semantics here is quite different. If you would do this in Python with a range, you would do for I in range 2, comma, n plus 1. Because in the range function, the ending value is not included. So here it is included as it would be in MATLAB. Okay, so you also see an illustration of the shortcut operator here. We already had it here. So just like in Python, you can write something like result is result times I as result times equals I. So you can do that in most programming languages, where Fortran is a notable exception. Okay. Apart from that, let's say little surprises. So if we have a range, and this thing here is an example of a range can have a start value, an end value, as here. So we start with 2, we end with n, inclusive. And then if you want the step size, that goes in the middle. So that's quite different from Python and extremely similar to MATLAB. This would be the exact same notation you would use in MATLAB. It has the exact same semantics as it has in MATLAB. So yeah, for Python people, this is a bit of a false friend and a potential source for errors. So don't get confused. The step goes in the middle. If you think of slicing in Python, then the step goes at the end. So yeah, it's a bit confusing. Okay. So this is going to work on iterables as well, basically for slicing purposes, as you would do in Python. Okay, so error handling is going to, error handling call to error is going to print its message to standard error, and it's going to stop the execution. So that is a rather drastic way of error handling that would be equivalent to a Fortran stop or assist.exit in Python. You can also use exceptions. So basically there's a whole family of exceptions. These two are fairly relevant. An argument error is typically something that in other programming languages is called an invalid argument. A domain error also exists. So if you call a function with a value that's not in its domain, then you generate that kind of error. How do we do that? We do that using the throw function. So notice throw is a function, not a statement, which is perhaps a little bit bizarre because, for instance, in Python, throw would be the raise statement. Raise is a keyword in Python, and it's actually a part of the grammar. Throw is a function in Julia. So that is weird, at least if you come from a different background. Fortran doesn't have exceptions, so yeah, we're done. That's easy. So what happens here? We create a new exception. In this case, it's a domain error. We can specify the value which we're talking about, and then a message. And that is the argument to the throw function. Okay. So if you catch an exception somewhere, you can rethrow it using the rethrow function. That is quite straightforward. And then we have try, catch, end. So basically the catch is going to catch the error, whichever exception is thrown by this factorial function, if it's called on -1. And then of course, the error is going to be such an exception, and you can ask for the value, for instance, and that would be the value of n. Okay. So again, not surprising, just like in most programming languages that have try catch, or in Python try except, there can be optionally a finally clause. The finally clause is executed anyway, regardless of whether an exception is thrown or not. So that has the same semantics as in other languages. Yeah, so that is indeed what I would have tried to use the Compiler Explorer in order to check the code which is generated by these two guys. And as Les apparently has verified, my intuition was correct that this will actually, certainly at a certain level of optimization, probably you need O2, no, maybe not. Yeah, you would probably need O2 to get the same, to get the exact same assembly code, but with reasonable optimization, this should give the same code. It does the same thing, so shouldn't be much difference. But again, what is rather cute is that the no, sorry, the recursion is not gone away. Sorry, that was not a correct remark. So forget the last part of the sentence. All right. So yeah, that's a little bit about error handling. Yeah, essentially you can create your own errors. If you need to do that, then that's entirely possible. Okay. Functional operators. So basically, then we're talking reductions, such as sum, which takes an iterable and is going to, yeah, unsurprisingly compute the sum of it. We have the same in Python. We have the same in Fortran. You can get the sum of all the elements of an array in Fortran just by calling the sum function. Similarly in Python, that would work. You also have product, and you have reduce. You have map. Maybe reduce, basically that is required to do a fold. So essentially you can use that to implement your own kind of reductor, as the name implies. And trivially, I could do a reduce using a sum, using a function that basically computes the sum of two numbers. And then adding a starting value, I can actually apply that to a list. Map, no surprise. Filter, no surprise. Zip, no surprise. All of this is doing the same thing as in Python. And you have some helper modules like iterations and transducers, which help you to further do interesting things. And there is the pipe operator, which I'm still jealous of that Python doesn't have it. So essentially, rather than nesting functions, as for instance, in one of the previous examples, I should have used that example actually, that would have made more sense. Let me see where it is. Here. So basically here we have a map function, and then we have the all function. And in a way, I said, okay, let's start from the inside out. So that meant we first had to think about the map and only then about the all. So in a way, if you're writing this code, it forces you to kind of first do the inner part and then add the outer part, and it's all a bit messy. So in that respect, the pipe operator is very useful because it is just going to let you do that from left to right. So basically in the order you think. And that, of course, is rather nice. So in this case, I'm going to create a range of values between 1 and 10, inclusive, and I'm going to apply a function. And in this case, it's just a lambda function, which maps the value to its square. Okay, so that means I will get a sequence of 1, 4, 9, 25, etc. up to 100. And this sequence is piped into sum. So I will get the sum of the first 10 squares of the values 1 up to 10. That's basically the idea. So I very much like this approach because it really allows you to think about transformations of your data, filter operations of your data, and so on in a more sequential way, rather than inside out if you use the if you use the normal function notation. So this is really cute. This is also something that in C++20 and C++23 was added for ranges and views in C++ STL. Okay. Let's talk a little bit about data types. So data types are pretty crucial in Julia, regardless of whether you use them directly or not. Indirectly, they're very important. So it's important to also understand how they operate exactly. So there are quite a number of basic types. And we have a whole family of integer types. And those of you familiar with NumPy will recognize those. Basically, we have an int 8, an int 16, an int 32, and an int 64. So essentially, that means you use 8 bits, 16 bits, etc., respectively, to represent your integer. So for int 8, that means you can represent values between -128 and 127. For int 32, you have values between -2 to the power 31 up to 2 to the power 31 minus 1. Similar for int 64. What you typically don't have in NumPy is an int 128. And to be honest, it's the very first time that I actually have seen this particular data type. So that's for really, really, really large integers. I don't really know why they have added this. Also because I didn't try it, but I'm again pretty sure that if you use this, you're going to be very unhappy about performance. So if you want to use that, make sure that you really, really have to, and that there is no alternative. So for each of these integer types, you have the unsigned equivalent, which basically means for uint 8, for instance, that you have numbers between 0 and 255. So essentially from 0 to 2 to the power the number of bits minus 1. Okay. Then there is the Boolean type, and of course just two values, true and false. So you would hope that that's represented by 1 bit, but that's not the case. There are no programming languages that allow you to do something with memory in chunks of a single bit. That's just not what the hardware does. Doesn't work. So essentially you need 8 bits anyway to represent the Boolean value. And that's obviously the same in all other programming languages as well. So it's not as if this is something specific for Julia. I'm just mentioning it because you might hope that somehow magically a Boolean value would be a single bit, but no, it's 8-bit. Okay, all of those things, so both the integer types and the Boolean types are part of a supertype which is called integer. Okay. Then we have rational numbers. This is interesting because this is not a native type in most programming languages. So you would have them in Python somewhere in the standard library. You have, I think you have something like rational, not entirely sure. Should I check it? Don't remember. But at any rate, you have rationals. And as you can see, there is something weirdish notation here. There is these curly brackets and then this int type. So that actually means that I can create a rational int 8. So that means that the numerator and the denominator are both represented by 8-bit integers. So I can create rationals of any size I like. For instance, if I need very large numerators or denominators, I could use rational int 128. So these curly brackets are basically denote that rational is a parameterized type. Okay, then we have floating point, and again we have quite a number of floating point types. We have float 16, float 32, and float 64. So float 32 is single precision. That means you get floating point values between minus 10 to the power 38 and 10 to the power 38. You have 7 significant digits. Float 64 is double precision, so that uses 8 bytes rather than 4 bytes. And basically that means values between minus 10 to the power minus 10 to the power 308 to 10 to the power 308, and you've got 15 significant digits. So on most CPUs, that's what you have hardware support for. Very modern Intel CPUs also support a float 16, so that's half precision. That would mean that you have something like 10 to the something, which now I can't remember, but anyway, you have 3 to 4 significant digits of precision. Why has this been added? Basically because of machine learning. So there is this observation that once you've trained a neural network, that you can actually sort of compress it to reduce the single precision values of the weights to half precision values. And that, of course, if the hardware supports it, can actually speed up your computation considerably, and will, of course, reduce the memory footprint of your model, which, if you're talking large language models with billions of parameters, really makes quite a difference, like a factor of 2. So that makes it an important type on GPUs. On CPUs, yeah, you should exercise a bit of care because it's only very recently that some GPUs, Sapphire Rapids, if I'm not mistaken, of Intel, actually support float 16 in hardware. So that means that if you use it on hardware that doesn't support it, it will work, it gets emulated, and you will have a performance penalty. Okay, so those are also part of a family of types which are called abstract float. Okay, and all of these together, so the integers and the abstract floats and the rationals, are all in the family of real values. So a real value can be an integer, it can be a floating point value, it can be a rational number, whatever. And of course, this is a language for scientific computing. So yes, complex is in fact a first-class citizen. And basically we have, again, complex F16, complex F32, and complex F64, which is unpleasant because basically this is different from what you would have in NumPy, in the sense that the names in NumPy, you also have 64, but that is 32 bits for the real part, 32 bits for the imaginary part. So a complex 64 in NumPy is in fact single precision, while a complex F64 in Julia is double precision real part, double precision imaginary part. So that is different. And it is a false friend. Of course, I'm not saying that Julia does this wrong, because there is this F here, which means that we are talking complex using float, That's what the F is for, 64. So there is nothing wrong with this. It's just confusing when you switch between Julia and NumPy. So yeah, be aware that that's the case. What you might be missing with respect to floating point and complex numbers, if you again are familiar with NumPy, is the float 128 or the complex 256, which would be quad precision floating point, quad precision complex. So they do exist in NumPy. However, no hardware supports it. So that means if you use them, you get a big performance benefit, a big performance penalty, sorry. So probably that's the reason why the Julia developers decided to totally skip on them and just not introduce them in the first place. Okay, so that gives you, again, confusingly, complex as a type. So don't ask why we have abstract float, but complex and integer. I don't know. I really don't know. No idea why they chose those names. Maybe because then complex and real are sort of the same thing. I really don't know. It's weird. Okay. All of those together are numbers. So this defines a type hierarchy. Number is an abstract type that can be either real or complex. Where's my mouse? Either real or complex. In its turn, complex is an abstract type that can be complex F16, F32, F64. Abstract float is, as the name indicates, very clearly an abstract type with float 16, float 32, and float 64. And integer is again an abstract type that can either be bool or int 8, int 128, uint, etc., etc. So this defines a tree of which the leaves are concrete types, and all the inner nodes of that tree are abstract types. That's basically how it works. And then, of course, we have characters. And as opposed to many programming languages, characters are not a single byte, but rather 32-bit Unicode characters. So strings in Julia are in fact 32-bit Unicode, which may or may not be a nice idea, depending on your point of view. But the name of the type is just character, char, basically. And then we also have strings, which are, of course, sequences of characters, and they have their own string, their own type as well. Okay, so for these type, we have literal values. If I just type 5, then that's always interpreted as an int64. If I explicitly want a constant value, a literal value that represents, for instance, a uint 8, then I would have to cast 3 to a uint 8. Of course, this is just something for the compiler. This is not something that will be done at runtime. If this is really a literal value, that is something that the compiler will do for us. So there is no performance penalty here. But uint 8 3 would give me an unsigned integer 8 bits. So basically, we also have this notation here. So 3/5. Don't get confused, Python people. This is not your integer division. This is basically the rational with numerator 3 and denominator 5. And again, unless I specify something different, this is going to be a rational int 64, which basically means that numerator and denominator are 64-bit integers. For floating point, this really annoys the hell out of me. So basically, it's the same as for C++, and C, if you just specify 5.1 that's going to be float 64. This I'm quite happy with. This is what I expect. If you specify 5.1 F0, then it's a float 32. Again, I wouldn't mind if it were not for the 0, which you have to, for some reason, add to that, which really annoys me. Because in C and C++, it's just 5.1 F, so I'll always forget the 0 in Julia. Why that's the case, nobody knows. Anyway, if we want complex numbers, the notation is also fairly straightforward. So we just append im, so for imaginary, to the imaginary part of our complex number. So this would be 5.1 real part and 3.0 imaginary part. And that would, again, give you a complex F64, so double precision real and double precision imaginary part. And the same, we have the annoying 0 for the F, and that would give us a single precision complex number. Okay, Boolean, easy, true or false. Yeah, so in Fortran you would indeed have to, and also not only can, but also have to. You can either use the notation which you specify, or in modern Fortran you would actually do it differently. So basically you would define a type alias and then append the alias to the value. So for instance, you would do something like, let's say dp is an alias for real 32, okay, 64 in this case. This you would define upon import from ISO Fortran env, and then to denote a constant, you would do something like 0.5 dp. So that would be the modern way of doing that in Fortran. But indeed, you can also use the notation which you suggest. With the D and the E, the D for double precision and the E for single precision. But yeah, I would really recommend the modern style for Fortran. But so basically it means that this guy here is indeed double precision. So if I do something along the lines of 5.1 E minus 5, that is going to be double precision. If I want it to be single precision, I should do it, sorry, with a bloody annoying F0, and then it would be, oh no, that was not be a good idea. Okay, let's see, I probably have to append it here then. No, also unhappy. Interesting. F0 not defined. Nice. Can I actually do this? Apparently not really. Interesting. I would really have to look that up. We can try it, but I don't think that this is going to work. Maybe this would work. That would make, yeah, that makes sense. Okay. What? No, that does not make sense, because that is just interpreted as no. So no, this really doesn't work. Okay, I would have to look it up how to do that with a power notation in single precision. Yeah. Okay. To be honest, I'd also not know how to do that in C++. I'd also have to look it up where you put the F in that particular case. I don't know, to be honest. Never needed to do that. So I would have to look that up. Interesting question. Okay, I'll modify that slide to actually give such an example because this is weird. So page 22, I want float 10 to the power something. Right. So Boolean is just true and false, lowercase, so not uppercase as in Python. So that's the difference. And then characters are enclosed in single quotes. So this is the same as you would have in C and C++. Characters are enclosed in single quotes, strings are enclosed in double quotes, and no, you can't swap that around. So if you have double quotes A, it's going to be a string, not a character. If you try to do single quote ABC space DEF, the compiler is going to say no. So that is very similar to what you have in C and C++. You can't swap them around as you can in Python, as you can in R, as you can in Fortran. They don't care whether you use single quotes or double quotes. However, in Julia, that's not the case. So for type conversions, it's very easy. Just use the type name as functions. So what I could always do, of course, is say, well, okay, let's write this as float 32 of 5.1 e minus 5. And now I have the single precision thing. Okay, let's try this, because that was actually what you suggested. So let's see whether it does this. It's happy with that. Okay, this is really, okay. Okay, and now I get it. Now I know why the F0 is there. Okay, right, learned something today. Great. Yeah, because you always write it with an exponent. The F is always followed by an exponent. So if you don't want an exponent, you have to put 0 because 10 to the power 0 is 1. Okay. In some universe, that makes sense. Okay. So string substitution, I already mentioned it. You can actually do quite a lot. So the $sign, if that prepends a variable, that will just be substitution. So in this case, what we will get as output, given that n is 3, is the string 2 asterisk 3 equals, and this we are actually going to evaluate. So this will evaluate to 6, and the result is put in the output. So basically, it would be this. Okay, this is very similar to Python, where you would in fact use curly brackets in order to evaluate an expression and use its value in an F string. So it's kind of the same, but here you actually have to type one character more than you would have in Python, because you need an opening round bracket, a closing round bracket, where you just need opening and closing curly brackets in Python. Well, yeah, okay. All right. And then, of course, we have data structures when things get more interesting, because that allows us to create our own types and to do more significant things than just compute with numbers. And the first type are tuples, named tuples, structures, sets, dictionaries, and arrays. Arrays come in two forms, vectors and matrices. So we will go through them one by one. So, for instance, for vectors, we have two types of vectors. We have column vectors and we have row vectors. So this would actually be a row vector. Okay. A column vector, sorry. And this would be a row vector. And of course, for MATLAB people, that makes a lot of sense. So basically, elements in a row are separated by spaces. Columns are separated by commas. So that's basically the idea. And then you immediately know how to specify a literal matrix. because that's going to be a sequence of numbers separated by spaces, which represent the row, then a comma for the next row, again numbers separated by spaces to represent that, another comma for another row, etc., etc. So this is actually notation which was borrowed from MATLAB. What you actually get is a 1 times 3 matrix for a row vector specified like this. So that already tells you something. What it tells you is that just like R, just like MATLAB, just like Fortran, matrices in Julia are stored column by column, which is different from what Python typically does in NumPy, where the default is row-wise storage. So that means if you translate from NumPy to Julia, think whether you're doing your iteration in the right order. If you are iterating over 2, 3, or whatever dimensional data structure, it's going to be different in Python versus any of the other languages which I mentioned, so Fortran, R, and MATLAB. Keep that in mind, it's important. Okay, so in a way, this is horizontal concatenation, if you want. That's what they term it. So a matrix, as I mentioned, would be the first row, the second row, and you can actually add commas. You can do it this way as well. Okay, so that's vertical concatenation. So in a way, space is horizontal concatenation, semicolon is vertical concatenation. Anyway, so this would give you a matrix. You can also have an array, and in this case, I would create an array, a 3-dimensional array with 3 rows, 5 columns, and whatever the 7 signifies. Whatever you want to call that, planes or whatever. And I'm creating an array where the values are not initialized. So undef means don't bother to initialize. I just want the memory reserved. The type of the elements is in this case float64. So that's another parameterized type. An array type is parameterized by the type of its elements, hence again the curly bracket notation here. Okay, then we have a lot of array functions. Many are familiar. For instance, zeros. You can guess what that does. That's going to create an array filled with zeros, similar for ones. For trues, for falses. So trues and falses would give you arrays filled with binary values, either true or false. You can fill an array, you can have a range, you can fill a random array with random values. So rand would be a uniform distribution between 0 and 1. Rand n is going to be a normal distribution with mean 0 and standard deviation 1. Okay, so for instance, fill 3.14 to 3 is going to create an array with 2 rows and 3 columns, and each element is going to initialize to 3.14. And that's a graphical representation of what you would get. Okay, you can also create a vector out of a range. In this case, I have a starting value of 5. I have an end value of 1, and I want 5 elements. And I want to collect that into an array. And so basically, that would give me this guy here. So this is in a way very similar to the linspace function in MATLAB or the linspace function in NumPy. Okay, don't forget to collect, because a range is a iterable, but not an array. So basically, you need to collect that into an array. Okay, so if you have an array or a matrix or whatever you want, Basically, there are quite a number of properties for that. One is the L type, which is the type of the elements. So you can, if you have some array which comes from somewhere, you can just ask, okay, what's your element type? And then that could be, in this case, it would be float 64. The length, which is basically the number of elements. In this case, you can ask for the number of dimensions, which for this particular one would be 2, because in this case, of course, it is a two-dimensional array. The length is 6. That's basically the total number of elements. And then the size is a tuple. So this is extremely similar to Fortran. Size 1 would give me the number of rows. Size 2 would give me the number of columns. And if I have a number of dimensions which is higher than 2, then of course it would make sense to ask for size A3, etc., etc. So this is actually just Fortran in a way. You can also ask for the strides. So if you ask for the strides of A, you get 1 and 2. Okay, so this is different from NumPy again, because in this case it is basically the number of elements that you move and not the number of bytes. So that is different. How do we interpret this? Well, to get to the next element in a column, you have to move 1 down. To go to the next element in a row, you would have to move 2 elements, because the array is stored column-wise. So if you would do the same with a Python NumPy array, then you would actually get something different. So basically, to move from one column to the next, that would be an elementary step, while moving to the next row would be the number of columns times the size. So basically that's a bit different. So again, if you rely on strides somewhere in Python, you would have to rethink that for Julia. Be aware of that. Okay, so that's why I put here not in bytes, as it would be in NumPy. Is this convenient or not? Yeah, I leave it up to you to decide that. Personally, I like to think in bytes, but okay. All right, so you do have a column-wise storage scheme here, so that is something that you really need to keep in mind. Okay, matrix operations, so essentially operational arrays, but you can think of those as matrices. So basically array indexing is one-based. Python people, be careful. So Julia is a language designed by mathematicians / physicists, whatever they are. So they like to count from 1 on. Python is designed by a computer scientist, and those people start at 0. Yeah, so basically for Fortran and for MATLAB, for R, there is no surprise. You start counting from 1 there as well. But for Python, C, C++, it's really different. So essentially, you use the square brackets to denote the indices you're using, and you have as many indices as the number of dimensions of your array. Just separated by commas. I don't think there are any surprises. The difference with Fortran is that you use square brackets, not round brackets. Similar for MATLAB, that would also be round brackets rather than square brackets. So in that respect, it's a bit a mix between Python and Fortran. Yeah, sort of. Okay, array slicing. So yeah, again, not many surprises. If you're used to NumPy, there are a few. So one is that if you do an array slice, you get a copy. That's not what you get in NumPy. In NumPy, you get an alias. So that's a big difference and something that you really have to keep in mind because it may have an impact on the performance of your code. Then another thing which is a surprise is of course the semantics of this expression. So in Python, this would start at 2 and end at 3 minus 1 inclusive. So here it starts at 2 and it ends at 3. So again, a very inconvenient false friend when you switch from Julia to Python and back again. So that's definitely something to keep in mind. Then scalar array operations. So if I want to multiply an array with a scalar, or add an array, add a scalar to all elements of an array, I would have to use the dot plus operator, the dot times operator, etc., etc. So that's quite different from MATLAB and NumPy. You do have the dot something operator in MATLAB, but that's the element-wise operation between vectors, between matrices, and so on. In NumPy, you don't have such a thing as a dot plus operator. So it's a very ugly false friend to MATLAB, and it's a trap for all and everyone in Python because you will likely forget the dot and get weird error messages. So the element-wise operations are also dot something. So that is in the same as in MATLAB. And now, of course, the dimensions must match. So basically, I can add a 3 by 3 array to another 3 by 3 array. So these are element-wise operations. Then matrix-matrix multiplication, that's simply the asterisk, so the star operator. But it's very easy. In Python, that would be, what is it again? Oh, what's the matrix-matrix operation in Python? Oh, damn. It's a while ago. Yeah, thanks. The add operator, exactly. Yep. Since Python 3.5, if memory serves, but indeed it's the add operator. So in Julia, it's just the star operator, very easy. And then again, the caret operator is doing the matrix power. So this is not an element-wise operation. This is the matrix power. So A to the power 3 means A times A times A. And of course, if you want to do that, it only makes sense on square matrices. And of course, if you do a matrix multiplication, the number of rows of the first array of the first matrix must be the number of columns. No, sorry. The number of columns of the first matrix must be the number of rows of the second matrix. So basically, dimensions must correspond. Okay. Element-wise functions, same thing. Don't forget the dot here. Otherwise, it's not going to work. And of course, interestingly, the dot is at the end of the function name, while for the operators, it's at the in front of the operator. Okay, I don't know. I really don't know. I really don't know who does things like that, but yeah, that's the way it is. Transposing a matrix or doing the complex conjugate in case of a complex array is using the quote. So that's pretty similar to MATLAB again. Then we have in the linear algebra module, we actually have things like the determinant, the inverse, eigenvalues, eigenvectors, SVD, etc., etc. Okay. So how do we do that? Using linear algebra. So that loads the linear algebra module. And then we can just do SVD of A, which gives us the the matrix which represents vectors, the S, which is diagonal matrix. So essentially here is just a one-dimensional vector, and then V, which is the other vector. And then basically I could, if I want to, reproduce the matrix by multiplying U with the S converted into a diagonal matrix, and then multiplying by the transpose of V. So diag matrix, that's the M, what's the M is for, is in linear algebra is SVE. So basically all those functions are defined there. All right, that was all I wanted to tell you about arrays. And perhaps this is a good time for a break before we start to talk about structures. So are there any questions at this point? Okay, if not, let's have a 10 minutes break. So I'll put something on the screen. Okay, I'll look at the chat in a second. Okay, because I can't switch. Well, I maybe can switch. I don't know, but let's see. So that would be 15. Okay, let's make that 15:55, and that's CET. Yeah, that makes 13 minutes something. So yeah, a bit more than 10 minutes, but okay. All right, let's have a look at the chat. Okay, so so for the for Python, this is NumPy. So the add operator is really not Julia. So basically, it represents the matrix product, the operator for the matrix product. For instance, in for NumPy arrays, and also for arrays which are part of the Python standard library. So that's basically the meaning of that. But that is really NumPy. Then is there some speed comparison between MATLAB and Julia? Without any doubt. However, at the moment I can't really point you to one, but probably if you just do a Google search on that, you would hit quite a few articles on that. However, be careful, because what you often see in these cross-language comparisons is that in favorite language A, every effort has been made to get optimal performance, while in not so favorite language B, we just use any crappy code which you can think of. So be a bit careful, be a bit selective about which source you believe, because yeah, speed comparisons are often also, benchmarking is also often done for political reasons. So yeah, be careful there. Okay, Python environment, what would be the difference between Julia and a JIT compiled? Yeah, so basically, if the Numba compiler has sufficient information, then it should be fairly close or even equal to Julia, in my opinion. So TorchScript is probably also a compiled down version of a PyTorch model slash a series of statements on PyTorch data structures. And again, I would expect similar performance. Mojo, yeah. Mojo is a pretty new kit on the block. It's interesting, but it's very early. So yeah, at the moment, let's say I would not be inclined to use it in production, and hence I'm also not going to give a training on something like Mojo until it matures a bit. It's way too early to start really using it in production on HPC platforms. Yeah, whatever. It's too new, basically. But as you can see, I am interested because if you look here, then you see that there is actually a Mojo kernel in my default notebook stuff. So yeah, it's interesting, but too early. If you accept a similar performance with JAX, etc., how is the GPU support of Julia? That is quite reasonable. So there is quite some support for GPU computing, either through some libraries or again through access to other machine learning frameworks. So basically, yeah, that would be that would be quite good. I have some training material somewhere on GPU computing with Julia, and actually that's also something I will develop more training material on in the future. But that is, yeah, for this summer, perhaps, if I get around to it. I would first like to do more training material on other types of GPU computing, mainly from C++, either using frameworks or using SYCL or something like that. So for heterogeneous computing. So it's a matter of priorities. But GPU computing with Julia is quite okay. Absolutely. At the end of the day, they just compile down to CUDA anyway. So yeah, if they get that more or less all right, then they will have more or less good performance. Okay. I would like to fetch a cup of tea before we resume, so feel free to type additional questions in the chat. No problem, but I'm going to grab some tea before we All right, let's continue. Okay, so there are a number of questions. If you say that through other libraries, you mean no, not necessarily direct binding to Python, but sometimes to libraries that Python has bindings to. So yes, you can call Python code from Julia. That is possible. It's not the fastest thing to do. So that's more like something you would do for things that are not performance critical, but not in general. But basically, many libraries which you use in Python are just Python wrappers around libraries that have been implemented in C++, Fortran, or whatever, or nowadays also increasingly in Rust, and that you can also call, because there are other wrappers for Julia, from Julia. So basically, that would actually be kind of the same thing. So if you import pure Python library, so not the underlying libraries, but the Python wrappers in Julia, you are likely to be unhappy with performance, because you kind of have the Python performance, not Julia performance, unless, of course, the Python layer is pretty thin. If the bulk of the work is done in an underlying library, so a library that is not implemented in Python but wrapped by Python, and the wrapper layer is pretty lightweight or irrelevant with respect to the runtime of the actual algorithms implemented in the core library, then of course it doesn't matter. But this is a question which you can't answer in general, because it really, really strongly depends on the library that is wrapped and on the wrappers, how heavyweight the wrappers are. So that is difficult to answer in general. You can't really do that. Yeah, so basically, I haven't experimented with it, but typically bridging to other languages, so FFI, foreign function interface, is reasonably easy to do from Julia, although I only know that from reading about it. I never tried it. So yeah, it's certainly quite okay, and it shouldn't be too hard. That's basically what I can tell you about it. But I didn't experiment with that up to this point. So yeah, that's something again for me for future exploration. If the let's say the uptake of Julia increases, let's put it that way, because at the moment we don't see that much uptake. So investing too much in Julia at this point is somewhat dangerous, because it might be that I'm just losing my time. Okay. So we've been talking about matrices, and of course matrices are very important in scientific computing. But of course also a lot of data is represented in different ways. And one of the data structures which you want to use would be something like a tuple, or something that in Python speak you would call a data class without any extra methods. In C or C++, that would be a struct. In Fortran, it's a user-defined type. So essentially, that is, let's say, a type that has members which may or may not have distinct types. So in this particular case, we create a type that represents a pixel. And it's a pixel in a two-dimensional space. So we have an x and a y coordinate. We are also assuming that a pixel is at discrete points in space, so it's not something continuous, hence it's an integer. And we also assume, again, that we don't have negative values for the coordinates of a pixel, which might make sense, for instance, on a screen or something like that. And we represent the color for some reason by a string. The reason is mainly that I just want to show that if you have a struct, that the members not all need to have the same type. So we've got 2 uint 32, and we have 1 string member. And again, the notation is the same. So X, Y, and color are the names of the members, and the types are appended using this double colon notation. Okay, struct, name of the struct, and in between we have all the members. Okay, so I can create a new pixel just by using the name of the type, and then of course initializing each of the members. So the X coordinate of this pixel would be 3, the Y coordinate would be 7, and the color would be blue. Okay, so you can think of, if you like, pixel as sort of a constructor here. It creates a new type. Sorry, a new thing of that type, a new value of that particular type. So we can access the members with a notation that's familiar to you. You just use dot and then the name of the member which you want to access. So this would print the color of P, so blue, to standard output. What does not work, and that may or may not be surprising depending on your background, you cannot assign to a member of a struct, because structures are immutable. That's a little bit weird at first sight. However, if you come from a Python background, you actually might not be surprised. Because if you have, for instance, a named tuple in Python, then that's also immutable, like any tuple in Python. So by default, structs in Julia are immutable. So we can use the values, but they're set at creation time, and they cannot be modified at a later stage. So we can use the value, we can't assign to it. On the other hand, if you want a mutable struct, it's very easy to make. You just prepend the keyword mutable to struct and you get a mutable struct. So if I have such a pixel, then I can create it in the exact same way. I can use the attributes in the exact same way, and I can assign to an attribute, and that would work. So basically, by default, structs are immutable. If you want to make them mutable, you have to make that explicit. Okay, it's a choice. Whether it's a nice choice or not will depend on your point of view. Of course, you can already guess that the compiler is probably able to do smarter things if a struct cannot be modified. So you might get better performance if you don't need mutability, that it's not there. So that's the reason why it's a conscious decision to make something mutable. Okay, whatever. Type hierarchies. So as I already mentioned, in fact, we have quite a lot of abstract types in Julia. So we talked about abstract float, we talked about real, we talked about number, and so on, integer. All of those are abstract types. And if you define your own type hierarchy, you can also create abstract types. For instance, I can create the abstract type abstract point. Okay, so this is at this point just a name. Okay. What I can also do is create abstract subtypes of abstract types. And this is done using this notation or using this operator, depending on how you want to call this. So I'm going to, again, create an abstract type. In this case, an abstract 2D point, which is a subtype of abstract point. So less than column is in fact the subtype operator, is a subtype of. Okay, and I can create another one. I can also create an abstract 3D point, which would also be an abstract point. So abstract 2D point and abstract 3D point have a common parent abstract type, which is abstract point. Okay, so this allows us to create entire hierarchies of types. So just like Java, you can only subtype from a single type. So if I compare this to the object-oriented world, it would be that you have single inheritance, like in Java, not multiple inheritance like you would have in C++ or Python. Fortran is also single inheritance. Okay, at the end of the day, we need concrete types, and those can be subtypes of abstract types. So for instance, our mutable struct point2D would be an abstract 2D point, which means that it is also an abstract point, because abstract point is a point that has abstract 2D point as an subtype. So again, the name of the type here is point2D, and it's a subtype of abstract 2D point. And this is a concrete type because it's completely described. It has two members, x and y, which are both real numbers. So note this is real, so this can be integer, any integer. That can also be a Boolean, which doesn't make much sense in this case, but okay, a Boolean is an integer is a real, so yeah, it could happen. It can also be floating point. So at this point, we have a concrete type that actually can store quite a lot of coordinate types in a way. Okay, so you cannot subtype from concrete types. That is not possible in Julia. So any parent type of a concrete type is by definition abstract. So that was what I meant when I mentioned that the type family in Julia is a tree. First, it's not a DAG, a direct acyclic graph, because a type can only be a subtype of one type. So that makes it a tree. And what I also mentioned was that all the leaves in that tree would be concrete types, and all other nodes, so all inner nodes, are abstract types by definition. That's how the type hierarchy is defined in Julia, and that's how things work. This is nice because it makes life easy in the sense that if you have single inheritance, that is sidestepping a number of difficulties which you may encounter if you have multiple inheritance, both from the point of view of the developer, because if you have multiple inheritance, you get interesting behavior, and you have to know method order resolution and things like that. So a single inheritance does away with that. So that is an example. That is an advantage. What would be the root type? That's actually a good question. I remember that I looked that up at some point. I don't think there is such a thing as the absolute root type, actually. And no, there is no bottom type, because any bottom type, in a way, yeah, there are bottom types. Any bottom types is a concrete type. That would be a bottom type. But I think that you should view the complete type system of yeah, I'm pretty sure, I'm absolutely sure that you should actually view the type system of Julia, okay, as a collection of trees, so rather as a forest. I don't think there's a more abstract type than a number. So I think that's the top of that particular root. Just like here, the top of the tree here, so the root of the tree here is a type which I defined, abstract point. So it doesn't have a parent type. It's not derived from anything. So basically this defines a new type tree. So essentially I should modify the previous phrase that you should view the a type hierarchy as a forest, a collection of trees. So there is no root thing like you would have object in Python, for instance. Okay, now we have our point, and we have a concrete point, so we can actually start doing things. So what is good practice in Julia is that you don't manipulate the members of such a struct data type directly, but rather define functions which do that on your behalf. So in object-oriented terms, that means that in order to access the attributes of an object, you would use getter and setter functions. A getter function to get the value of an attribute, the setter function to set the value of that attribute. You would typically not directly manipulate the members of an object. In Python, for instance, if you define your own class and you want to indicate that you expect people to use the attributes of an object from that class only through setters and getters, you indicate that by prepending an underscore or a double underscore to the name of that attribute. So it's a convention, and it's actually the same in Julia. So you're not supposed to directly interact with x and y. You are actually supposed to do that through setters and getters, which if you define your own data structure, your own mutable struct, that you actually define those getters and setters as well. So here's an example. We have get x, and that takes an argument of type abstract point, and it just returns px. So this is really, really simple. Okay. Note that the type of p is an abstract point. So that means that a concrete point can either be an abstract 2D point, that the concrete point can either be a 2D point or a 3D point. Okay, then we have a setter, set x, and notice the exclamation mark. So remember the convention in Julia that if a function modifies its arguments, that you append an exclamation mark to the name in order to denote that, to stress that this is a function that modifies its arguments. And again, we have an argument p, which is an abstract point, and of course a value which is real. Okay, and that will simply set px to value. Note that we can have such a one-liner function with a begin and an end. And of course, to do an assignment, we would have to do that because this assignment defines the function. Just putting there px equals value would terminally confuse the Julia compiler, and it would tell you that your expression is nonsense. Hence, we assign a block. So we have a begin end block, and that is the body of our function setx exclamation mark, which simply assigns value to p of x. Okay, no explanation needed for get I and set I. It's the exact same thing. And now something interesting. For get z, that only makes sense when we have a 3D point. So rather than have abstract point here, which can either be an abstract 2D point or an abstract 3D point, this setter and this getter only makes sense for an abstract 3D point. So that's why then there is a typo, I think. Let me verify. Point 3D. Yeah, that should be abstract 3D point, not abstract point 3D. So yeah, that's a typo which I have to fix. But anyway. Okay, so why would it fail? Let me just show you what happens if you were to type that. Where's my Julia thing here? So basically you would have something like f, which takes x as an argument, and I would define it as x dot something equal, oh, okay, let's do x, y, because I need to assign something. X equals to y. Okay, this is something the compiler is not going to like, because you've got these two equality signs. What are you doing? So the syntax says, okay, if you have something like this, just enclose that in, come on, enclose that into a begin end block. So like this. And now the compiler immediately sees, well, okay, this is a function assignment, and this guy here is going to be the body of the function. And the statement in the body of the function is going to be, sorry, this thing here, which is an assignment. So no confusion between the assignment to the function, which is the function definition, and the assignment here, which is an assignment to, in this particular case, some number of some variable x, which is whatever I never specified. Okay, so yeah, this is the syntax which you are supposed to use. Otherwise, compiler unhappy, you unhappy, you have to figure out what goes wrong. Okay, so apart from that, this is interesting because now if I were to try and get z, so use the getter for z on a 2D point, the compiler would not let me do that. The compiler would say, okay, you can't do this because you said that get z should get a 3D point as an argument. You're giving me a 2D point, I'm not going to do that. So you see where this is going. So this leads to code that will fail at compile time. Okay, so already mentioned it, do not access field in structures, define accessor methods. It's a convention, nothing more. There is nothing that would prevent me from directly setting a member of a mutable struct. If I want to do that, I can do it. So this is just a convention. However, it's strongly recommended by the Python, by the Julia development community to adhere to this particular convention. Okay. So basically, now we have methods on types. Okay, so method doesn't have the meaning in Julia that it has in object-oriented languages. In object-oriented languages, if you have a member function, let's put it that way, of a class, that is typically called a method. So for instance, if I take the example of Python, and we would have an object of type dict, so a dictionary, then there is a method get. Okay, so that would be a function defined in the class dict, somewhere deep in the Python source code. So that would be the meaning of method in the context of object-oriented programming and languages that support that programming paradigm, so that allow you to create classes and so on. So a method basically means something different here. It is actually an instance of code that the compiler generated for a specific type. So, and that is also what multiple dispatch is in fact based upon. So we have a function distance, and we define it on two arguments, P1 and P2, and both are abstract 2D points. Okay, so we, just for convenience to simplify the notation here a little bit of the distance function, we just get x1, y1, x2, y2 using the getters. I could do that immediately here as well, but yeah, that would obfuscate the formula for the distance, which I wanted to avoid. Okay, so this will work for any point, well, sorry, any concrete type that inherits somewhere in its hierarchy from abstract 2D point. Okay, I can do the same distance function, but now for abstract 3D points. And then, of course, I can, in addition to x and y, also get the z coordinate. And of course, my distance formula also is updated. So basically, I've got a function distance with two methods. One method is defined, well, one method is used if the two arguments are abstract 2D points. The other method is used when the arguments are abstract 3D points. Okay, so basically, this is the meaning of method in the context of Julia. It is a concrete instance of a function on concrete types at the end of the day. So that's what that actually refers to. Okay. So one of the things that is really, really annoying if you have in an object-oriented language single inheritance, or in the context of Julia, is okay. What are you going to do with things that share properties? Java, for instance, solved this problem by introducing, besides classes, also interfaces. And the class may implement an interface, which basically means that it implements a number of functions in order to be compliant with certain functionality. So in some programming languages, that's called an interface. In other programming languages, that's called a trait. And that's also a trait is the terminology which is used in Julia, and actually also from time to time in C++, although you would probably use the term the concept there, but okay. So what is a trait? It's a property of a type. So at the moment we have our 2D point, we have our abstract point, our abstract 2D point, our abstract 3D point, and we also have a point 2D, so a 2D, two-dimensional point, which just has x and y coordinates. Now, what if I wanted to add a color property to that? Okay, what I can do is create a subtype out of point 2D, because point 2D is a concrete type. I can't subtype concrete points, concrete types. Cannot do that. Julia doesn't allow that. So how do I deal with, on the one hand, with a point that doesn't have color, and on the other hand, with a point that does have color? Okay, what I can do is use traits, use properties. So what I can do is say, okay, I'm going to create another abstract type. And in this case, it's colored style. Okay. So then I can actually create a concrete type is colored. It's a struct is colored. It's an immutable type. It doesn't have any members, but it's a concrete type that is a subtype of our abstract type colored style. Okay. And I can correspond the opposite. So I can create a type which is not colored. Again, it's just a struct, immutable struct, no members, and it's a subtype of colored style. Okay, this is bizarre. So what do we do in that? Okay, the first thing we do is we specify default behavior. And the assumption which we make is that nothing is colored unless we specifically make it colored. Okay, so if I create a function now which says, well, okay, colored style of any type is not colored. Okay, so what's this is not colored? Well, essentially, it's the function that creates an instance of type struct is not colored. this is not colored is that is not colored, that is not colored is a struct. So this function is just going to construct a struct which is of type is not colored. Okay. So if I apply colored style to any type at the moment, the result is going to be a struct is not colored. All right. Now, if I want to define an action on a trait, I can actually do that. So for instance, if I want to get a color of something that is colored, okay, so that's the function that I'm going to define. So I've got an argument which is some object of some type t, which is an unknown type at this point, but it has to, there is a condition on that. So basically, t is a type, variable if you want, and that's done with this where curly brackets thing. So this indicates that t is a type parameter. So this is a function that is defined on abstract types, not on abstract types, on type parameters. Okay, so the function getColor is defined on t. GetColor is applied to a function colored style t. So I'm going to convert t into a colored style. Okay, and that is going to be applied to object. All right, so we're not there yet. This was quite abstract. Now we are going to be more concrete. So if I have, I create another function method, getColor, but this one is actually defined on an isNotColored object. So basically here, t is converted into colored style, which can either be colored or is colored or is not colored. So if due to this function call t is converted into an is not colored, then I just throw an error because I'm trying to get the color of something that has no trait color, that is not a color, is not colored. Okay. On the other hand, if code style converts t into is colored, then we just get the color attribute of object. Okay, so how do we use this? Because this was the definition of a trait, so we still need to use that somehow. Okay, so we create a mutable struct picture, a pixel, which has an attribute string, a color, which is a string. Okay, now I say that I define the function colored style if the type is a pixel, then we invoke the isColored constructor. Okay, so I create a pixel and I can happily call the getColor method on pixel. Let's go back to the previous slide and see why that is. I invoke the getColored pixel on an object of type t. Okay, t is a type parameter. Right, I'm going to apply colored style to t. T is pixel. Okay, let's go back here for a second. If I apply colored style to something that is derived from pixel, okay, then we invoke isColored. Okay, so this guy here is going to invoke isColored. So I'm going to call getColor with an instance of a struct isColored and the object. Okay, so I have to look here because the first argument here is an isColored. Okay, so that's the one I'm going to call. That's the method, the getColor method I'm going to call. Object is my concrete pixel, P in the next slide. So I do get P.color and I get the color. So here it is. That's how it works. So I have added the trait isColored, the colored style trait, if you want to be more precise, is the colored style trait. I have made pixels isColored. Okay, so that gives you blue. If, on the other hand, I have a point, which is a 2D point, and I ask the color, okay, what's going to happen? So point in this case is point 2D. All right, I call getColor with point. Let's move back to the previous slide. So this is the getColor method with a single argument. Okay, so that's the one which is called, and object is a 2D point or a point 2D. Okay, so T is going to be point 2D. No problem. We ask to convert to call the colored style on point 2D. Okay, and that is going to be a problem. Well, it's not going to be a problem because point 2D has never been given the trait isColored. So basically it's this function call which applies. This method definition here of colored style. So it's just a default. And the default is the constructor for is not colored. Okay, so that means that getColored in this case is called with an instance of is not color and my point 2D. So we get to this method of the getColor function, the second one. So the first argument is of type is not colored. The second type is whatever object. So what happens is the execution of error that this thing is not colored. So if I call getColor on a point 2D, I should get an error message. And that's indeed what we get. Okay, so this is kind of nice. Runtime error or a compile time error? That will be a compile time error. Wait, will this be a compile time error? No, that's going to be a runtime error. Yeah. Well, yes or no? Just a second, let me think for a moment because no, it's a compile time error. Because you have the whole typing thing. We have the type at compile time, so that should give a compile time error. Yeah. Okay, so what else can we do with traits? Well, for instance, I can make something entirely different that has nothing to do with pixels or points or whatever. I can make that colored. For instance, I think the example is paint. Yeah, exactly. So I can define a struct paint that has a color and maybe other member attributes, I don't care, but basically it has a color. And then I register the trait by indeed saying that if the function colored style gets an attribute of type which is derived from paint, that then it should use isColored. Okay, so paint is also colored. So if I do paint is paint yellow, and I do print line get color on paint, then the exact same thing is going to happen as I discussed with Pixel. So basically, the first method gets invoked. The first getColor method is invoked because it has a single argument. The type is going to be parameterized and it's going to be paint. Paint is going to be going to be used as an argument in color style. Colored style is going to return isColored. isColored is going to return an struct is colored. So the third method of getColor is invoked, where we have as the first argument an isColored struct, and as a second argument the object. So we get object.color, and that is being returned, and we print yellow. So that's basically the idea here. So this approach allows to, in the same way as you would in Java use interfaces to, let's say, glue on functionality to types that are absolutely not in a type hierarchy. So basically, that allows for attaching traits to certain types. And that's done through registration, if you want, through this abstract type colored style. And then the concrete types is colored and is not colored, which are both concrete types derived from colored style. Is that more or less clear? This is, of course, using multiple dispatch to a very large degree. So, and this actually also allows you to do many things that you would otherwise use object-oriented programming for, specifically with class hierarchies. You can do this in object-oriented programming as well, but then you would need multiple inheritance. So, for instance, in Python, you could happily do this. It's not a problem. If you would do this, it would, in Python terms, be called a mixed in, and that would be the way to also apply traits to classes in Python without having to force classes into the same class hierarchy. So here we do the exact same, but we do it based on type hierarchies. Okay, great. I do agree. I mean, I share your sentiment that thinking in terms of trait is awkward at first. So when you first are confronted with this traits thing, you think, okay, what the heck is this? I was a bit used to it because in the first place, I've been doing, back when I was very young and very naive, quite a lot of Java programming, where you face the same problem. It's solved in a slightly different way, but essentially it's the same thing. You have you suffer from the fact that you have single inheritance only, and you have to have a way around it. So the way around it that Java defines is interfaces. The way around it, you do it in Julia because you don't have classes, is through the type hierarchy and through multiple dispatch. But essentially, the expressive power which you get from multiple dispatch and thinking in terms of traits is the same as you would have in object-oriented programming. Through class hierarchies or through what you would do in Python, for instance, mix-ins or some form of duck typing, which you can get away with. And you would do the exact same thing in C++ as you would do in Python. So the expressive power is quite the same. I don't see many differences, but it's a totally different way of approaching something. And it's alien if you're not used to it. Then it takes a little getting used to before you get the hang of it. But I rather like the idea. After a while, then you get used to it, and it's actually quite powerful. So you have, in my opinion, the same expressive power as you have with an object hierarchy, but you also have the same problems as you have with an object hierarchy, which is something that initially the Julia people denied and said, no, multiple dispatch combined with traits is much easier than class hierarchies and such, and it simplifies development. Yeah, as long as you have rather simple class hierarchies and you have a small code base, yeah, then it's simple. But then object-oriented programming is simple too. So once things get complicated, they get just as complicated with this approach as they get with object-oriented programming, and you just face the exact same problems, which I personally thought would be the case when I read about it first. Thought, oh wow, they are wildly optimistic, and indeed it turns out they are. Okay, so basically there is no a type relationship between Paint and Pixel. They don't share anything except the colored style trait, which we added. So that's basically the idea. They share trait, they don't share type. Well, parent type, ancestor type, whatever. And so that allows for what in some programming languages you call duck typing. You can do that in C++ using templates. You can do that in Python in many ways. So basically, this is the same thing, but now using multiple dispatch and class hierarchies. Type hierarchies. Okay, more or less clear? All right, parametric types. So we actually already did some parametric types. We used them, but we didn't really explicitly create one ourselves. So we can actually do that. So both abstract types and concrete types can in fact be parametric. So basically here we have two parameters to our type. One is the coordinate type and the other is the color type. And as you can see, they're specified using curly bracket notation. And they will be specified in that way as well as soon as we make things concrete. So X and Y will be of coordinate type and color is going to be of color type. And that basically means that I can create a pixel where the coordinates are specified in uint16 and the color is specified as a string. And then, of course, I have to initialize it with the appropriate integers. So I have to call the uint16 function on these integers to convert them into the appropriate type. But of course, I can also make another pixel that has float64 as the type for the coordinates and a uint8, which essentially would be a grayscale value for the color. So that would work perfectly well, no problem. Okay, so again, you can do multiple dispatch on abstract parameterized types, which in fact we did when we were talking about the colored style thing, because that the traits are in fact implemented that way. Okay, so that was what I wanted to tell you about how to design software in a composable way, how to achieve the same things which you would normally achieve using object-oriented programming, using what is essentially a mix-in in object-oriented programming languages, and combined with what we would do with duck typing there. Okay, any questions about this? Because after that we switch to different topics. So again, I realize this is weird. Just out of curiosity, is there anyone who finds this, let's say, natural in some way? Just out of curiosity, because, yeah, depending on your background, you might say, yeah, okay, this is obvious. Yeah, not really. Yeah, I would expect, to be honest, that there is no one who finds this a natural way of expressing things. Yeah. Okay. Yeah, that would be my intuition. I'm not sure from what background you should come. Ah, yeah, maybe. If you have a background probably in Haskell, then you might find this again fairly familiar, because they do things in similar ways. But anyway, who knows Haskell? So okay, right. Let's turn a little bit to something different and something which, in a way, is a little bit boring. Yeah, so that's the drawback. Rick makes a very pertinent remark. The amount of reusing function names makes it pretty complicated. Yeah, that's true. And of course, that also means that that finding the function which you need may take quite some digging. And that is one of the things that, in my opinion, the developers of Julia, when they said, "Oh yeah, our multi-dispatch thing is much more transparent than object-oriented programming," yeah, as long as you have a few methods to a function, if you start to have like 10 methods or more to a function, it's going to be complicated. It's going to be error-prone. It's just the same thing as in object-oriented programming. Why would the law of conservation of misery be broken by Julia? I mean, come on, what do you expect? So, okay, but then again, yeah, exactly. So basically, Haskell, of course, has been designed to be a functional language, and it has been designed to be sure that type inference actually works. So a lot of very hard thinking has gone into the design of the Haskell programming language by people who really know about computer science. While Julia has been, forgive me the expression, cobbled together by people who are not computer scientists. And I noticed that in several places. So yeah, basically that means that the design is suboptimal in some places. You see the same, to be honest, in MATLAB. You see the same in Maple back in the days. I only know of, for me personally, there's only one exception to the rule that if non-computer scientists design programming languages, that they typically do a somewhat suboptimal job, and that is Mathematica. That's, in my opinion, the only language which is really well designed and was not designed by someone with a background in computer science. I think that Wolfram did a lot of reading on computer science, but he is a physicist. He's not a computer scientist by education, but he definitely read up. While developers of MATLAB, no, not at all. Developers of Julia, yeah, I really don't think so. So yeah, you notice it somehow in the design. Things that should work don't work because, yeah, no clue. And yeah, okay, anyway, it's there. It has its function. It does very nice things. So let's be clear about that. This is not intended to be derogative about Julia as a tool. It's just that, yeah, for me, the design hurts my eyes at some points because I know you can do things differently. But okay. I/O. So, well, you can do many types of I/O, of course, and the simplest type of I/O which you can do is text I/O. And as usual, we have streams. We have a standard in stream, we have a standard out stream, we have a standard error stream. No surprises. You also have file streams. So I do like the syntax of this. So you open a file, and in this case, we open it for writing. The file name is myfile.txt, so no surprise there. And then we have do file. So this is a little bit like a context manager in Python, where you would have with open something as file, and then a block of code. So this is the same. This do end block will in fact define the context of a file. So I rather like this approach. This is well stolen from Python. Okay, syntax looks different, but it's the exact same idea. And so basically here I'm just printing to this file line by line, and I'm just printing something x followed by the square root of x. And again, I'm using string substitution here to make life easy. Okay, so quite straightforward. How do we read? So again, we have the open do file thing. So basically do end, and then we read line by line, and we can do that using the each line index, the each line function of file. So the each line function is very similar to what in ancient Python, so Python 2 dot something, you would have achieved with the read line function. Nowadays in Python we don't have to bother, but back in the days it would have been somewhat similar. So essentially each line is going to be an iterator. In each iteration of the for loop, line will be assigned a line, and if memory serves, including end of line of that particular text file. So quite straightforward. And then you can do something with line, whatever you want. Okay, so this is nice, and that's also why I was referring to Python context managers, because this acts like a context manager. If you treat file streams this way, then at the end of this do block, the file will automatically be closed. So that's the exact equivalent of the Python with open as file context manager. So that is really nice. Okay, there is also a module which is called printf, and that would give you formatting capabilities like you are used to certainly in MATLAB, I think in R as well. Okay, this looks very weird to Python people. Essentially, it's the syntax which you would use in C, in the C print statement as well. Hence, also why it's called printf, because yeah, that's what it's called in C. Okay, one thing to notice is that this is not a function. This is a macro. So basically, besides functions, Julia also has the notion of macros, which are in fact text to text or source code to source code translations of certain expressions. And so that's the case for this printf thing. So that's invoking a macro on a series of arguments. So basically, the first thing is a formatting string, and all the other arguments are in fact things to be printed. So %.1f means this is a floating point value, and I want one digit after the decimal dot. %.f5f means, okay, this is again a floating point value. I want 5 digits after the decimal dot, so for the square root of 0.1. So this can be convenient. You need to load that module, and then it actually works. Notice this is a macro, so no brackets here. Okay. Bit more performance, binary I/O. So actually similar. We open the binary file for writing. No difference. Again, the do end with file. And then we use the write function. First argument is a file that has been opened for writing, and the second argument is whatever you want to write. So basically, this is going to write double precision values in binary representation into your file. Similar for reading, no surprises. We specify read, and we use the read function. And what we need to specify is the file and also the type of what we want to read. So that means that, but this is fairly obvious, if you have a binary file, you need to know what's inside there. There is no automatic conversion or anything like that. So basically you just need to know. And so you simply read until you read the end of file. So the end of file function EOF is going to check whether the file is, whether you've read the last byte of the file or not. So basically while you're reading the file, you can use the read function. While you're not at the end of the file, okay, you can use the read function. Okay. So obviously there is a whole ecosystem of modules for doing I/O for specific file types. So for instance, there is a module for delimited files. So that means your typical CSV file, comma separated values, tab separated values, etc., etc., etc. All these types of simple text files can be read with functionality in delimited files. Output formatting I already mentioned, that's the printf module with the macro. Then there's also a module for dealing with HDF5 files, which is unsurprisingly called HDF5. So that's quite useful. It means that an HDF5 file which you generate, for instance, in a machine learning thing, can actually be read easily from within Julia. Okay, there are many more modules, but these are the ones which strike me as the most useful in general. Okay. Any questions about I/O? I would say it's unsurprising. I like the do end thing, which manages the context of the file. So yeah, well stolen from Python. Okay, code organization. And now we cycle back to a question which was asked at the very beginning of the session. So how do you organize your code? You organize your code in modules. And of course, all the modules which you are using are in fact also organized in this kind of way. So modules are namespaces. So that answers the question which was asked at the beginning of the session. So basically I can specify a module that will typically live in a .gl file, and the name of the module in this particular case is very originally my functions. The module begins here and ends with the end statement. We can define any number of functions or structs or abstract types or whatever we want. We can define in a module. So here we actually have two functions. One function is called fac, the other function is called GCD. Okay, we know them, we implemented them a while ago. But we add one thing to the module, which is actually optional. So we do an export fact. Okay, that has a consequence. Let's see. So fact is exported. GCD is not exported. Okay. So essentially, you can also do this in Python. You would have to define dunder all on a module, which says, well, okay, these things are exported when you do an import. So you have an equivalent in Python, which is not really well known. So what's the consequence? It means that if I'm using my functions, fact is exported, and I can immediately use fact. So on the other hand, if I were to try to use GCD, for instance, of 3 and 17, then the compiler would say, oh, no way, I don't know what GCD is. Still, I can use the GCD function by prepending the namespace. And the namespace is just the name of the module separated with a dot. So I can use the GCD function in the context where I've been using my functions, but I need to prepend the namespace. So as a module developer, I can, let's say, control what you directly import. So basically what you can import without having to use a namespace qualifier, and for which functions you need to explicitly use a namespace qualifier. So that's under your control as a developer of a module. Okay. I can be more restrictive. So for instance, if I use a module and I only want to use the fact function, then I can specify that by specifying here a comma separated list of functions or data types or whatever that I want to explicitly import into my default namespace. So again, just as you do, for instance, import from math import sqrt in Python, it would also be a good idea to do to use using my functions fact so that you don't pollute your namespace with whatever. Yes, so basically if two modules export the same function, then indeed multiple dispatch may or may not decide which one to use. So basically if they have the same signature, then of course there is no criterion to choose between one and the other and you will get issues. So basically then you would have to be a bit more careful when you use the using statement and do an alias so that you're sure that if you're calling one, that is the one you actually intend. But that's the same as, for instance, in Python. You would have the math module in the standard library and the CMath module for complex arithmetic. Well, for complex mathematics. Both have a square root function. If I do import, if I do, which I never should, but okay, from math import star, and I would do a from CMath import star, I would definitely have an issue. Because then I have two implementations of this sqrt function, for instance. One will not function on complex numbers, and the other will happily do that. So that's the same problem. You would face the same problem here. Sometimes, indeed, maybe many times, I don't know, you would be saved by multiple dispatch because those functions with the same name would operate on different types. So yeah, that's possible. Then the right thing will happen. If not, you would have to use aliases, as we'll see in a second. Okay, I can also import my function fact, and that does something different. So basically that means that I can do that if I want to add methods to the fact function. If I just use fact, then I can't add methods. If I import it, then I can. So that the semantics of this is quite different. Why did I format that code in this way? That's weird, but okay. Anyway, so this would be the way to get around the problem which you mentioned, that you have two distinct implementations which could not be discriminated by using multiple dispatch because they have the same signature. Then you can define an alias. Again, this is very similar to Python. Okay, so I have to fix some stuff here on page 39 as well, on slide 39 as well, because that is ugly. Okay, and the order of the thing is not right. So if I want to implement an additional method to the fact function, for the fact function which is defined in my function, then I'd have to use import. Otherwise, I'm using. Sorry for the feeble pun. Okay, I could have a minimal package, GCD, and I can use the package manager for that. How do you get into the package manager? If you're in the interpreter, which I'd have to start here, because that one is driving a notebook, so let's start Julia here. I can get into the package manager by typing a closing square bracket. And then you see my prompt changes to package. And then I can do all kinds of package commands. For instance, generate a package or install a package. I can do that from this prompt. I get out of this by typing Control C. Now I'm back in the Julia interpreter. Okay, so one of the things that I could do in the package manager is generate a new package. And that would look a bit like this. So you would have a description of that particular project, of that particular package, which is a TOML file. And you'd have a source directory with a essentially empty, well, not an empty, Julia file with module GCD and maybe some example function. I don't think so. So essentially the TOML file would look like this. So it would specify the name of this particular package, which is GCD. It would specify a unique universal identifier, which is really a unique identifier. So no two Julia packages will ever have the same sequence of characters here. This will always be unique. You specify the authors. Essentially, you can have a list of authors. Each author is a string, which is the name followed by the email address or whatever you want, essentially, but this is the convention. And then you also specify the version of that particular package. Okay. Then you make sure that your source code contains something useful. And what you should do, if you want to use that that package, is that the parent directory of GCD is in the Julia load path, which is an environment variable. Typo on slide 40, project. Okay. TOML. Wait. 40. That is TOML. Where is it, typo? Yeah. Yeah, but the problem is I don't see it. I understand what you mean, but I don't see it. There. Yeah. Here it is. Yeah. Okay. Thanks. Got it. Yeah. Sure. I was looking here and thinking, nah, that's TOML. Okay. But yes, indeed, in the file name there, yeah, I should indeed correct that as well. Thank you. Okay. Right. Okay, so basically you have to make sure that the parent directory of whatever you want to use is in fact in the Julia load path, which is just an environment variable which you can set either in Windows or in Linux depending on your operating system. Okay, documentation. So basically the documentation is a little bit like in Python. So essentially, we have a triple quoted string. Where did we see that before? And then basically any explanation you have about this particular module, or this, in this case, this particular function. So the what's it called? The convention is similar to Java. So the documentation of the function goes before the function definition, not inside the function definition as it's the case in Python. So again, a bit of a false friend, which you may get annoyed by if you switch from one to the other. And what you can put in there is anything markdown you want. So basically, it's pretty straightforward. Okay, and actually here, this is formatted code. So basically this says, well, okay, format this in such a way that it is syntax highlighted and so on, if this is possible. There is a repository of packages for Julia. So if you go to the Julia website, julialang.org, no, I don't want to install. I want to have the menu. Where is that? I think I have a reference to that in the slides somewhere. Because it doesn't seem to be here. Let's wait until we get to the slide with the references, because I think it's there if memory serves. Otherwise, I'm dreaming it up. That's also possible. So basically, if you ask for the help on that function, you would get something that is nicely formatted in Markdown. So basically, you get something which looks pretty nice. Okay, so the ecosystem. Basically, you have the package manager, and essentially that knows where to fetch packages. So essentially, it can be used to install packages, to deinstall packages, to also create specific environments for certain tasks. So that's rather nice. You also have this printf, which we already mentioned, the limited files and so on. Iteration is also nice. That gives you lazy iterators, which is always a good thing. Third-party libraries, one that I like is benchmark tools. So that helps you to benchmark Julia expressions. It's a little bit like the Timeit magic in Jupyter Notebooks, but it's a little fancier and it really looks nice. You also get a distribution of times and so on, so it's a very useful tool. Struct arrays is also quite interesting because it allows you to convert an array of structs into a struct of arrays, which you may want to do for performance reasons. And that module actually does that sort of automatic for you. So you don't have to rewrite your code. You just have to use that module in order to do a code transformation, or to have Julia do a code transformation. Then there is Getfly, which is a plotting library. Data frames, which unsurprisingly implements data frames a la pandas or a la R data frames. And you've got argparse, handling of command line arguments, can be useful. The name is suspiciously similar to the standard Python library module argparse, but okay. So basically, you have quite a rich ecosystem, and of course, it's growing every day. So basically, you can install all these tools through the package manager. So that is quite convenient. Benchmark tools is quite useful. So that's one which I certainly want to stress a bit. So conclusions. Good, bad, or ugly? Well, basically, it's up to you. I've tried to give you features of Julia, an overview of its features, an overview of what I consider strengths, what I consider weaknesses, what I consider not so well implemented. But up to a very large degree, that's of course a personal interpretation. And it depends on taste. It depends on your history as a developer. Which programming languages are you used to? How much did you buy into a certain paradigm? How willing are you to step outside of that paradigm? Okay, I'll go back. I'll come back to that immediately. So the question is, what's my opinion about using Julia to implement, to develop HPC applications at scale? So basically that use MPI, for instance, that use multi-threading and so on. So that is entirely possible. For instance, at HLRS, so the Hochleistungs HLRS, what's the R for? Rechenzentrum Stuttgart? Yeah. So basically the HPC Center of Stuttgart University, they are developing an HPC code that is written from scratch in Julia. And if I could remember what it was, I think it's some GCD code. It's Lattice Boltzmann, I think, at a large scale. And I'm not entirely sure, to be honest, because it's a while ago that I heard about that. But I think it's a pretty large, well, a pretty scaled up Lattice Boltzmann code. So yes, it's definitely possible. Is it really the way to go? Okay, that's a different question. That depends on the uptake of Julia as a whole. I'm not sure, to be honest. If I look at questions we get about Julia, it's still very, very limited. If I look at, if I compare the number of participants to this training with the training on C++ or with the training on Python, Python wins hands down. This is a bit more than C++, but yeah, the C++ people want to start using C++ like now, while I'm guessing, I don't know, that quite a number of you are just here to get a little bit of an overview of what Julia does and then decide whether you want to go there or not, which is not the case for the C++ training. So in that respect, I don't know. I'm still not convinced that in the long run, Julia is going to make it. They are trying to break into the machine learning and the AI space. Well, okay, I still prefer machine learning space than AI space, but whether how successful that is and how competitive they will turn out to be with Python, I'm really unsure about. Because at the end of the day, for that kind of applications, if you use something like PyTorch or you use something like TensorFlow, Keras, whatever, yeah, you have a very thin layer of Python, which may be really, really slow, but you don't care because at the end of the day, it wraps extremely optimized CUDA libraries or CPU libraries, whatever, that give you excellent performance and have nothing to do with which programming language you're using in order to drive the process. So I don't know whether Julia has an edge there. I don't really think so. So that's at the moment, I think, their best path to success. But whether it's worth it, I don't know. Really, I have no idea. I'm not overly optimistic. I'm also not pessimistic. If I were pessimistic, I wouldn't do this training, period. So I still believe that Julia can play a role not only in scientific computing, but also in HPC. Whether that's a long-term thing, I don't know. Embedded programming. Frankly, I don't think anyone is using it for that. The problem is basically that if you are really into embedded programming, that you will want your executable to be directly on the embedded device. And the problem is that the executables which you, well, the executable code that you generate with Julia are kind of generated on the fly. And yeah, that gets cached, but it only gets called from Julia. So I don't know. So I would say, I would think not. I don't think anyone is doing that. But if I were into embedded computing, I would probably still go for either C or nowadays maybe for Rust. But I'm not into that at all. So I shouldn't venture too many opinions, but Julia, I don't think so, to be honest. What's my opinion on Julia versus Python for the purposes of scientific computing? It strongly depends on what you do. So the big advantage of Python is that it has really a huge and extremely diverse ecosystem. So I can use Python. For instance, if I'm a data scientist, I can use Python modules to talk to my relational my relational database systems. I can use Python to talk to other types of data sources, such as document stores, such as Redis, such as Redis. I can use it to get things from the web. I can use it to do REST API calls to whatever service. But I can also use it to scientific computing using either Pandas for data analysis or NumPy to solve differential equations, whatever. So basically, it's an extremely rich and diverse ecosystem. So that's the very much the selling point for Python for me. And so typically that's a good thing. Julia is trying to get there, but of course it has, let's say, years and years of history missing, and a much smaller developer community. So yeah, in that respect, it depends a little bit. Now, for raw speed, which is of course performance, which is of course what we are interested in scientific computing, with Python, pure Python, you're not getting there. Just throwing in NumPy is probably also not getting there. So depending on what you do, if you really develop a substantial code base yourself without relying on high performance libraries, then of course the problem is that if you want to get the performance with Python, you'd have to use tooling. You'd either use Numba in order to also generate C code, C++ code on the fly, get that compiled and run that, load that dynamically and run it from your Python application. Or you would have to even go a step further and use Cython in order to achieve the same, but with more control over what you're doing. So that is a bit of a drawback in a way, or not. It's a bit more hoops to jump through with respect to Julia, where it's actually done out of the box anyway. So yeah, in that respect, Julia definitely is a strong language for scientific computing. The heart of the matter is, will it survive? Because, of course, scientific computing is a fairly small domain. Who is going to invest in Julia? That's essentially the question. It honestly seems that, like you, yeah, that's a bit the problem. Julia kind of lacks a selling point. I mean, if I just use Fortran, it's not significantly harder than using Julia. I have arrays as first-class citizens, which is what I like. I have an ecosystem of libraries, which is what I like. For pure scientific computing, yeah, I'll get excellent performance. And I just use Fortran, period. So that's one thing. For Python, you can argue about data science and the huge ecosystem, blah, 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 the whole thing, which is sort of a unique selling point if you want. But for Julia, I don't know. I mean, it's a language that will generate you fast applications that will have good performance. But is that a unique selling point? I don't know. There are other languages that do that as well. I can achieve that in Python. Okay, I have to go through a bit of effort, but I can also achieve good performance. So yeah, I don't know. It's kind of, again, like an alternative to, it feels mostly like an alternative to MATLAB to me. So in that respect, you could say, okay, MATLAB people will feel at home with Julia and they'll switch away from sponsoring networks to using an open source tool. Maybe that's the best selling point. And of course, it really scales to HPC applications, where MATLAB, well, no, I don't think so. So in that respect, it will outperform MATLAB, definitely for real HPC applications. But yeah, is that then again a unique selling point? I don't know. So yeah, I would agree with that statement, to be honest. Okay, so wait, I will have to switch here because it's going a bit too fast. Okay, then Nishant is saying, I've come across the expression that the edge of computational speed with Julia over Python comes only when the written code is fantastic. Well, no, not really. So basically, the advantage of using something like Julia, like NumPy, is that actually you get easily code which a good compiler can do nice things to. That's the advantage of scientific computing. In a way, our code is simple. Okay, don't get me wrong, the problems we solve are hard, but the code we typically use to solve them is fairly straightforward because we do matrix-matrix computations. Okay, we are not going to implement them with the triple for loop. We are going to implement them or use them using the star operator. So yeah, as long as we express our mathematical models in terms that are fairly straightforward to a compiler, we will get good code. We will get good performance. So I don't think you need to write exceptional code in order to get good performance with Julia. You just need to use Julia well. So one of the things which you shouldn't do is iterate over an array and do something element by element if you have an element-wise function. That is not a good idea, but that would also not be a good idea in MATLAB. That would also be a terrible idea in NumPy. So basically all the advice which MATLAB developers give you, all the advice that NumPy developers, well, not NumPy developers, but users of NumPy give you, it also applies to Julia. So basically, if you use common sense, don't do weirdish things, then you will get good performance out of the box with Julia. There is no reason why that would not be the case, in my opinion. Okay. Then a question by Sibe. That's indeed something I came across. Yeah. Developing my own scientific computing code base and having to refer to Cython. Yeah, exactly. Yeah, that is a problem. Have a look at Numba because it can give you comparable speed to Cython in quite a number of situations, and it's much easier to deploy in the sense that it's just decorating a function. That function is going to be compiled. There will be a wrapper for it, and basically, it's going to use decorators. So that might be interesting to look at as an alternative to Cython if you can get away with it, because not everything you can do with Cython can be done with Numba. Numba is kind of a black box. You decorate your function, you cross your fingers, you hope for the best. Cython is a much more precise tool where you really can use type annotations and so on to your advantage. You can do that in Numba, but it's like it's much less precise. Okay, manual embedding. Ah, there is something on embedding. Okay, and just out of curiosity, what are they saying? Because truly, embedding is not my field, so I've never done that, and basically, I don't know. So okay, they claim it can be done. Okay, fine. I'm happy to believe them. How well it works, I really don't know. I should not try to venture an opinion. But yes, apparently it's, well, at least they claim you can do it. How well it compares to C code, I don't know. Probably they will claim that it's very good, but I don't know. Okay, then for AI applications with Julia or Python is more preferable. Python ecosystem is larger. Julia is trying to catch up. Again, most machine learning libraries or most machine learning modules, let's say, or packages in Python will rely on underlying libraries which are optimized to that and implemented in C++. So I would not expect a performance benefit from Julia. So unless you like Julia as a language, I would opt for Python because of its larger ecosystem. And if you already know Python, then yeah, for me, the choice would be fairly simple. But again, it's a matter of taste and a matter of especially seeing whether the functionality you need is available in Julia. What I also assume is that if there is a new kid on the block in machine learning, either a new algorithm or a new type of layer or something like that, you will find it first in a Python library and then maybe later at some point in a Julia library. So again, yeah, I don't know. I would go for Python. Julia seems quite nice for simulations. Yeah, sure. Yeah, good performance. Yes, easy to write. Indeed, it's kind of as easy or easier than Fortran. So yes, absolutely. And not a lot of libraries you can depend on in other languages. So don't get me wrong, Julia does have a rich ecosystem. Only, of course, Julia is like, I don't know, 7 years, 8 years old by now. Python is 30 years. So of course you have more Python libraries just due to the time it takes to develop stuff. So, but Julia has a really rich ecosystem. So don't get me wrong there. It's quite okay. The better option for machine learning than Python, but yeah, no, I don't see where it comes from either, to be honest. I really don't see it. It's a claim which I see is made, but for me, that's basically partisan reasoning. That typically comes from the Julia community, and yeah, that's fine. I mean, claim whatever you want, but yeah, I'd like to see figures, numbers that prove that, but I don't see those. I get claims which are typically not really substantiated, or which are based on a very specific library or a very specific thing that I want to do. But yeah, prove that it's in general better. And I'm happy to switch to Julia for machine learning, but up to now, I don't see it, and I don't see why people claim that even. So no, to be honest, no. Okay, I naively spent a lot of time in the past with Java. Yeah, that was a bit of a that was a bit of a how shall I put it? A flippant remark. So yeah, I did spend a lot of time doing things in Java, but I was doing quite different things. So basically, I was the code which I needed to develop, and then we are talking end of the 90s, beginning of 2000, was actually to be cross-platform. To do cross-platform development in those times was not that easy with traditional programming languages. And Java was a good choice for that. At the time, the standard library which came with Java was also very extensive compared to some other programming languages. Java gives reasonable performance, of course not as good as C, C++ or Fortran, but it's reasonable. And it's definitely a lot faster than Python. In those days, Python was also absolutely not as developed as it's now, and it was positioned as a scripting language as opposed to a real programming language. So basically, at the time, Java was a good choice. If I were to do the same type of research right now, I wouldn't use Java ever again. So the choice was okay in the context of the time, but I would not make that same choice right now. A similar mistake if I spend a significant amount of time in Julia instead of in another language. That is a very hard question, and it is very context dependent. So one of the reasons to get fluent in a programming language is what career opportunities it offers you after you get your PhD. I'm assuming here that you're a PhD student or postdoc. So essentially, if you stick to research and you stick to your research field and Julia survives, which, as I already mentioned, I don't know. I hope it does. It's a nice language, but maybe it doesn't. I can't predict that. I don't have a crystal ball. So then there is no objection to spending significant time in Julia, because things that you learn in a certain programming language transfer to other programming languages, not directly, but in spirit they do. If you know about multiple dispatch in Julia and you know how to use traits using that, you can apply that immediately in Python by using mixins. You can apply those same concepts in C++ again by using mixins. So essentially, the concept is the same, only the concrete implementation is different. But conceptually, the same thing exists in those other programming languages. So if you're used to think in those terms, it's very easy to make the translation step from Julia to C++ or Python, or vice versa. So I don't necessarily think it would be a mistake. Now, if you say, well, okay, after my PhD, I'm going to work for a bank, or I'm going to work for an insurance company, yeah, maybe not Julia. Then I wouldn't do so. So it depends on what you have in mind with the rest of your life. That's basically somewhat critical. Okay, HPC applications, they generally advise you packages to be installed by a specific compute node. Yeah. So again, that depends quite a lot. How do you install your packages? Do you install them from source, or do you install them through Conda? So yeah, that's the first thing to realize. If you manage your own packages and you do that using something like Conda or Mamba or whatever, then basically what you're downloading are wheels. And wheels are pre-packaged binaries, libraries or whatever. And so basically that means that you will get code that does not run optimally. So essentially it doesn't matter on which node you install it, because it's going to be pre-packaged binaries, pre-packaged binary libraries. So yeah, where you install them, it doesn't matter at all. However, if you install from source, then yes. And then of course your code gets compiled, and the compiler will, if you ask it to do so, optimize the code for the processor on which you're installing. And hence it makes sense to do that on a compute node. But again, the answer is a bit nuanced, so it depends on how you work. So indeed, Julia would sort of solve that, except that you have to be a little bit careful, because the just-in-time compiler of Julia will cache, which means that if it has generated code once, it's going to use that code. So basically that means that if you test your software on one type of node and then run it on another type of node, and you don't clear that cache, it's not going to be recompiled, and it's going to either crash if you move from an older node to a newer node, from a newer node to an older node, or potentially run suboptimal if you compile on an older node and run on a newer node. So basically, the just-in-time compiler doesn't necessarily solve it unless you are aware of the caching and make sure that you don't have caches at the moment you start running your code, so that indeed everything gets compiled on the platform which you're using it on the specific node you're using it on. Then I would actually guess that Julia is better than Python at handling sloppily written code, as there should be more optimization opportunities. Yeah, because it's compiled. Yes and no. So it depends on how sloppy the Julia code is written, in the sense that if you use inappropriate typing, you will actually get suboptimal performance as well. So that is something that the compiler can't solve anymore, can't correct anymore, because you're forcing it into a specific route. So that's basically the problem there. In conclusion, would we say that whatever scientific programming can be done in Julia can also be done in Python with the same computational efficiency? In Python plus helpers, like Numba, like Cython, the answer is probably yes, but it might require more effort on your side. So indeed, installation through Conda means that you download wheels, and that means you get pre-compiled code which is not optimized wherever you install it. So basically, it doesn't matter at all where you install the packages using Conda, because you will get the same on any node. It's just pre-compiled code, not optimized for the architecture you're running on. That's very simple, very straightforward. So if you want to benefit from compiled code optimized for the node you're running on, you would have to install from source so that actually something gets compiled. And Conda doesn't do that. Conda just downloads pre-compiled stuff. Nothing is built on the node itself, in general. Okay, JIT compiler with removal of cache. Yeah, exactly. Yeah, absolutely. That ought to be the case. Of course, comparing apples with apples, so the underlying code should also be reasonable in Python. So basically, you should have the same algorithm implemented in the same way, both in the Python package and in Julia. Otherwise, you're comparing apples with pears, and that doesn't hold water. But assuming that the implementation is the same, yes, then typically you would get better performance from Julia because it's compiling on the fly. If you are careful about the caches, as you mentioned, then you would get by Conda and just installing a wheel. Yeah, absolutely. Okay, let me, before too many people leave, just quickly do a screenshot here, because otherwise I don't have an attendance list, and then the people of the secretary's office are going to kill me. So let's quickly grab this. Okay, now where's the thing? All right. Why is Do Not Disturb on again? I don't want it on. Okay. I will look at questions in a second. I just need to do this now, because otherwise I get killed by secretaries, which is an unpleasant death. So I would prefer to avoid that. Let's see, where is the thing? No, I can just put it here. Okay, so Julia 2024. What are we? 0307. Yeah. 01. Okay. Go. And the second part of this, which is like all of this, and again, screenshot. Okay, and save the thing. That should be the one. Nope. Yeah. Okay. Save it. All right. Bloody stick to the place where I last saved this. Okay. Then Julia. All right. And not one, but two. Okay. And there we go. And gone. All right. Chat. Let's have a look. Yeah. Okay. Yeah. So yes, attendance certificates will, for KU Leuven people, automatically appear in your whatever portfolio thing. For other participants, it will normally be mailed. So that's done by the secretary's office. So as soon as they have the actual participants list, which I have to pass to them, then you would actually receive it. So that can take a while, but normally, yes, you would receive it. Yep. So this session has been recorded. So if you want access to the recording, just let me know by email and I'll send you a link. Okay. Any further questions are, of course, very welcome. But if not, I wish you a very pleasant evening, and I'll see you maybe in some other training. My pleasure.